We are live. Welcome, everybody.
All right, sounds good.
Yeah, let's throw our names as Taglik / Joshua did. Let's throw our names. Yeah, let's throw our names. Group chat right here in the Hangout itself. / Joshua did. Let's throw our. Whoa, look at delay, huh?
Yes.
All right. Let me check. Let's make sure the YouTube stream is actually.
Yeah, it's working for me.
Wow, we have this like inception of streaming going on right now.
Yeah. Make sure to mute one of them.
All right. Awesome. Well, thank you guys all for joining and trying this experiment. I am obviously not well set up for this kind of thing, as demonstrated by the blinding light behind me. Didn't even think of, I don't have another light handy, so you're just stuck with this horrible glare and 20 minutes late and all that good stuff. So I've been a big fan of Urbit for at least a year, and I've spent a lot of time reading and rereading the white paper. It seemed like an easy way to start a virtual meetup of some kind. I think there's probably lots of other things that we can discuss or present, but this seemed like a great way. Reading the white paper, it seemed like an easy, great way to get started, and the delay is just awful. So I think the best way to do this is for me to kick it off and maybe read the first summary, maybe a little bit further than that, and then anybody who wants to and who's in the actual Hangout, throw your name in the Urbit chat or the Hangout chat, and I'll kick it over to you, and we'll just get through as many sections as we can. Periodically, we'll check the chat for questions, because I think we're going to have to kind of manage the audio going on and off of mute, because there's been feedback already a bunch of times. So put your questions in the chat, and I'll try to check that after like every paragraph or something like that. Let's see here.
Do you want to accept questions vocally, like with interruptions, or no? Do you want to hold them all to the end of the section?
Put them in as soon as they come up, and I'll try to like check on paragraph boundaries, I think is the best way to do it. Some of the stuff, so section 1 is nothing, right? Section 1 is 2 pages, it's just a summary. It's just, we'll run over the Urbit summary, and then after that, we might want to have a conversation there. But after that, each paragraph, it gets really dense really fast. So I think that we don't want to go too long without checking questions or discussion, because I don't think we all just want to drone on. So without further ado, I put links to the white paper all over the place. You guys want to see the white paper on the screen while I'm talking, or you want to stare at me?
Oh, everyone has the white paper, so.
All right, it'll be me.
Yep.
Very good. Okay.
Mm-hmm.
Let's do this. So,
is anyone else having a huge amount of echo? Is that just me?
Oh, everyone has the white paper, so.
All right.
It may be an issue with your mic or speaker setup.
Testing 1, 2. Yeah, I think we just have to manage the mute going on and off, which is an incredible pain, but what are you going to do? All right. Whew. 25 minutes late. We are off. All right, Urbit, a solid state interpreter. And this is from a little over a year ago. I will skip the abstract. Section 1, Introduction. What is urbit? We can answer 6 ways: functionally, formally, mechanically, productively, securely, and practically. Urbit is a new, clean slate system software stack, a non-preemptive OS written in a strict typed functional language, which compiles itself to a combinator VM, drives an encrypted packet network, and defines a global version control system. Including basic apps, the whole stack is about 30,000 lines of code. I will note that that's actually no longer the case, and it's more like 40 or 50,000 lines, depending on how you count. But there are a lot more comments than there used to be. Let's see, formally. Urbit is an operating function, a general-purpose OS whose entire life cycle is defined as a pure, frozen, small function on its input string. The function is an interpreter. It compiles an initial language, which boots an initial kernel. Everything but the lifecycle function can upgrade itself from source code in the input string. You know what? I'm just going to keep checking the top. Let's see. All right, structurally, Urbit is a solid-state interpreter, an interpreter with no transient state. The interpreter is an ACID database. An event is a transaction in a log checkpoint system. The Urbit interpreter runs on a normal Unix server. It interacts with the Unix user on the console or via Fuse, with other Urbit nodes, in its own protocol over UDP, with the internets as an HTTP client or server. And again, this is all just summary. Securely. Security problems are an inevitable consequence of unrigorous and/or complex computing semantics. Rigor and simplicity are hard properties to enforce retrospectively on the classical Unix IETF W3C stack. A new stack designed as a unit, learning from all the mistakes of 20th century software and repeating none of them, should be simpler and more rigorous than what we use now. Otherwise, why bother? One example of painful heterogeneity inherited from the current stack: the relationship between a database schema, a MIME type, a network protocol, and a data structure. The same semantics may be re-implemented incompatibly at 4 layers of this stack. The programmer is constantly hand-translating values. Helpful tools abound. ORM is the Vietnam of computer science. But no tool can fix architectural impedance mismatches. There are always cracks, bugs, and attackers slip between them. Check in here. Productively. Urbit is designed to work as a personal server. This is not yet an established product category, so let's explain it. Everyone is a personal client, a secondary kernel isolated from the OS, the browser. Almost no one has a personal server, but they should. Urbit is a browser for the server side. It replaces multiple developer-hosted web services on multiple foreign servers with multiple self-hosted applications on one personal server. Why attack this problem with a clean slate stack? Arguably, what stops people from running their own servers is the usability challenge of administering a Unix box on the public internet. The Unix internet platform is 40 years old and has built up a lot of complexity. Mechanical simplicity does not guarantee humane usability, but it's a good start. A clean slate personal server with its own encrypted packet overlay network can forget that Unix and the internet exist. It can run on Linux and send packets over UDP. It can both provide and consume HTTP services, but its native stack is not affected by 20th century design decisions. HTTP services? Since a new network has no network effect, a node must find its first niche as a client and/or server on the old network. For its earliest users, Urbit has 2 main roles: as an HTTP client, a personal API aggregator, which organizes and controls your own data on your existing cloud accounts, and 2, as an HTTP server, personal publishing and identity management, blogging, archiving, SSO, etc. But Urbit still differs from existing web application platforms. and that an instance is designed to serve one primary user for its whole lifespan. And then practically, and this has changed somewhat from a year ago, but it is still, I think, generally accurate, and that is urbit is a working code in a semi-closed alpha, self-host, maintains a live network, runs a distributed chat service, which we've all been bouncing on and off of, and serves its own website and proxies everyone else's. One really important thing to note about the white paper is that not only is it's distinct from the state of urbit a year ago, but there are sort of separate, there's the maintenance branch and master on all the primary source code repositories, which each have diverged somewhat substantially from the state of urbit a year ago. So it's best to think of the white paper as the platonic ideal of urbit, and it's there are some distinctions between the system designed in the described in the white paper and the various current states of the system. There's also some things in the code samples that aren't quite right, and so that's our introduction. Let's see, do we have any questions? You want to just pass it around the room? Anybody? Maybe it's a good time to talk about how people got here or people's first reactions, because that's a pretty good summary of urbit right there. Anybody? Going once, going twice. Okay.
I have a question, actually.
Shoot.
When it here, his entire life cycle is defined as a picture of a small function on its input stream. We're talking about it's not talking about Argo there. It's talking about the virtual machine, which is called Knock, right? Because Argo, when it's done, is not going to be frozen. I mean, Argo will be continually updated, right?
Yes and no. So for now, with the current state of the system, what you're saying is correct. There's a lot that can change above knock. Knock itself is very unlikely to change unless you know, the bar pub can make his case to reverse Lubians. But the hope for the higher level systems, and this is articulated in more detail as we go along, is for them to be freezable, but they don't have to be frozen. So you're right that basically everything above knock, with a couple of exceptions, can be upgraded and is frequently upgraded over the air. But the design is, the hope for the whole system is that not only the VM knock, not only the network protocol AIMS, not only the operating system Arvo, the language Hoon, that all of these system level components can be eventually completely frozen. Now, user space would change, applications, integrations, things like that. And there's been some discussions about how you would make allowances for crypto updates. And again, I'm just a fan here, so I can't really speak to the intentions, but to the best of my knowledge, the goal is for the VM, the language, the network protocols, the OS to eventually be completely frozen.
Okay. Thank you.
Sure.
Is that addressed any later in the white paper?
It is somewhat. There's more detail on the forum. Curtis had a post recently about the versioning scheme and some of the goals of it. This was one of the things that really bothered me, frankly, when I first started reading about urbit, was this notion that you can freeze software. You know, it goes against what everybody else tells you from everywhere. Even I can't think of his name, Nuth, with the tech and the LaTeX system. That's the version number of LaTeX, I believe, is pi. So each subsequent change adds another digit of pi. So the idea is convergence on only maintenance fixes, bug fixes, security fixes, no new features. And the idea is sort of adding, as you're adding more digits, the software is getting more and more frozen. But it still makes allowances for changes. And the idea behind Kelvin Zero is that you're completely frozen. Now, I don't know what will happen if you run out of kelvins. My assumption is you add a decimal place when you get to, you know, Kelvin 4, and it's obvious that you have to make more changes. But I think the real idea of it is that for there to be a pressure. As the system gets more mature, you want to make fewer and fewer changes. If you're going to make a change, you know, the bar for disrupting any of these things has to be really, really high. One of the other documents, the community constitution, which is on urbit.org/post, talks about over time transitioning update policy to the Congress of star owners. And again, I think that that's also a very long-term vision. But it's easy enough to imagine that, you know, say Hoon gets to 20K or 15K or something like that, that there would be really intense and in-depth conversations about making any changes at that point. But it's frankly one of the, there's so many things that are counterintuitive or simply go against established best practices in the whole Urbit project, and Kelvin versioning is one of the most substantial ones, I would say. All right.
Don't forget to check the chat.
Yeah, the system's slowing down. I'm gonna have to start shutting off some software here.
Yeah, I must admit, actually, Kelvin versioning is one of the things that fascinated me most about the Urbit project when I was first starting to read on it. This, you know, it's kind of the Martian thing is kind of a flight of fancy, but you know, you think about, you know, if civilization is still around in 1,000 years, we'll have had computers for 1,000 years. At some point, we'll have come up with infrastructure that just works.
Hopefully.
And so,
I mean,
you know, we kind of speculate what would that even look like.
I mean, we've had hammers though for how many thousands of years, and they're still making new innovations in hammers though.
Like what?
The ones with mercury in them, or the little ball bearings, so when you hit them, they don't bounce back at you. Those came about 20 years ago. I mean, there's tons of innovation in hammers.
Wow, I certainly never heard of that.
Yeah, so it's actually really great, because when you hit, no matter how hard you hit it down, it won't bounce back up and hit you in the face.
Wow,
interesting.
Hey, Keith. I see him in the corner.
Anybody else?
I'm sure that maybe Keaton and Palfin can probably speak about.
What's up, homies? Yeah, I just joined the convo apparently. Yeah, a question on kind of the long-term stuff regarding infrastructure or whatnot. Yeah, I mean, I guess like in general, like the whole point of being able to update this thing over the wire is to basically adapt to whatever kind of underlying hardware infrastructure may or may not come about in the near-term future. And then the cool thing about making this kind of virtual layer is, of course, that not only can you update everything on top of that layer of NOC, but you can update everything beneath that as it relates to the bare metal stuff. So I mean, it's definitely not out of the question that pretty soon, you know, I don't know, then the next, if Urbit does become successful and there are some pretty cool hardware innovations, yeah, like Urbit could have its super optimized hammer for running NOC or something.
Well, that is a good point. You know, going back to your comment about, you know, innovations in hammers, there may be innovations in hammers, but the basic tools of carpentry, you know, that you still use hammers. And so there's that definition of what a given tool is. And so even if we've got, you know, whatever kind of hardware we're using 1,000 years from now, we could still make it work we could still make it, fit to the API or to the spec of the NOC combinator, for example.
Yeah, we see Urbit currently paving over the old internet to use as its own foundation. Maybe in the future, something else will use Urbit as its foundation for innovation.
So, like, in theory, if you had like the Kryptonian crystal, pretty much like a Martian crystal that just ran NOC, that would be Kelvin 0. And then from there, you build everything on top of that. Like I'm just saying, like from the perspective of 1,000-year computing type view, because that's what I kind of imagined. Like the crystal wasn't changed; it's almost like it's magic at that point. You still might know how it works and whatnot, but it's still kind of like magic, right?
Like technological sediment.
Yes, so to speak. Yes, sir.
And I would just add that NOC, in a sense, is an interface. NOC specifies the rules by which you determine that a correct computation has taken place. It specifies no algorithms. So as we'll see when we get to jets, obviously that's a really important part of Urbit. But that gives you a lot of flexibility going forward. NOC as the foundational interface, in some sense, is a comforting security blanket because it's incredibly simple. It's hard to imagine how it could be simpler. And so if you can build an entire system, an entire distributed, secure network on top of such a simple foundation, you should be able to adapt to just about anything that happens, at least in theory.
Yeah, I mean, I think the cool thing about NOC being so simple is it almost just kind of goes back to the core vision of this project is, basically allowing this kind of general purpose computing to be accessible by anybody. When you have this layer that's so fundamentally simple that like my mom or my grandma can understand it, and if that can scale, horizontally across the human population, I guess, then I mean, yeah, you might have super optimized, interpreters or super optimized compilers or super optimized hardware that this stuff runs on. But, that can be all abstracted away so long as you have this clean layer that is kind of this, as you said, this universal language that everything can plug into. So long as anything complex can be broken down into this pretty simple, understandable language, then it just kind of democratizes computing in general, which I think is really cool.
Is the goal to ultimately do away with jets, though?
I mean, I don't know. All of computing is a hoax, right? So jets are just less of a hoax.
One of the most interesting things on that front is Fodwhite Ragful's project Jacques. And Jacques is NOC on the JVM, but it's using an optimizing compiler called Gruffle. Truffle and Grawl are the two twin projects that are sort of research level projects for optimizing compilers on the JVM. And basically, if the project can be successful, what you would end up with is a NOC runtime that would only need jets for implementations that are algorithmically different from the underlying NOC. Now, if you actually look through the source code of the jets that are currently shipped with the interpreter, a lot of them use the same, exact same algorithm as the NOC formula or the Hoon source that they're paired with. The reason they're written in jets is that you skip the overhead of tree addressing primarily. And you just have direct function calls in C as opposed to having to trace through the subject and then match the core battery, and we'll get to all that, hopefully. The cool thing about this JVM project is basically it bundles a JIT that would be able to generate those those jet hotspots basically without actually needing to implement a jet for anything that uses the same algorithm. So the example everyone uses all the time is decrement, which is ON, and that's insane. You would still need an actual decrement jet. But a lot of the data structure stuff, maps and sets and things like that, you probably wouldn't need any of those jets. So that's a really interesting, still kind of a researchy project, but it's called JOC, and it's on GitHub, and I recommend everybody check it out. I'll throw a link up at some point. Okay, I am going to try to run through section 2, which is highlights and novelties, and then I'll be ready. Well, you can have another go round here, and then I'll be ready to hand off to anybody else who wants to read. So throw your name in the chat if you want to read section 3. And I'm going to keep going here. Section 2, highlights and novelties. Anything that calls itself a clean slate stack should be indistinguishable from a boot ROM from a crashed alien spaceship. Sometimes this is impractical. The aliens probably wouldn't use ASCII, let alone Unicode, AES, etc. There's a fine line between a metaphor and an actual hoax. And some designs are genuinely universal. An alien linked list is a linked list. Urbit also invents a lot of alien technical jargon. We admit that this is annoying. Abstractly, it's part of the clean slate program. Words smuggle in a lot of assumptions. Concretely, changing the words does indeed change the concepts. For instance, we say type informally to mean any one of 3 quite different concepts: span, mold, or mark. Before we review the design more systematically, let's take a quick tour of Urbit's more unusual architectural features, working upward through the layers covered in this paper: Nock, Hoon, Arbo, and Ames. Nock, the combinator interpreter. Nock, a non-lambda combinator interpreter, is Urbit's VM in axiomatic definition. Its informal spec is 340 bytes compressed. Nock is nowhere near the simplest possible definition of computing, but it's quite simple for a practical one. Nock is permanently frozen and will never need updating. A Nock value or noun is an unsigned integer of any size or an ordered pair of any 2 nouns. Nock is homoiconic, like Lisp. A Nock function is a noun. Nock cannot create cycles, so nouns can be managed without a tracing garbage collector. Nock is a little like Lisp if Lisp were only a compiler target and not a high-level language. As an axiomatic model of computing, Lisp and/or Lambda are an imperfect fit because the reduction axioms define high-level programming concepts such as variables and functions, which A, should not be coupled to the lower layer, and B, are properly human interface features belonging in the upper layer. Nock defines no variables, environments, functions, etc. It doesn't even have a syntax. Nock's only intrinsic integer operation is increment. Fancier functions are accelerated not by escaping to an intrinsic, extension, or native method, but by registering and recognizing specific Nock code blocks in the standard library, then matching their semantics with custom interpreter modules, or JETs. A JET may be implemented in native code or even custom hardware. It can have no side effects since all it computes is one special case of the Nock function. It is easily tested against the pure code. A more advanced system might use actual equivalence proofs. Hoon. Hoon is a strict, higher-order typed functional language which compiles itself to Nock. Nock acts as a sort of functional assembly language. The Hoon to Nock transformation is designed to be minimal, like the C to assembly transformation. Users often complain that the mathematical abstractions beneath functional languages are difficult to learn and master. Hoon is a low-tech FP language, which does not use category theory, lambda calculus, or unification inference. The Hoon style discourages aggressive abstraction and promotes a concrete, almost imperative style. Hoon inference works forward only. It cannot infer input type from output type. The inference algorithm uses manual laziness and a conservative work list algorithm, which terminates except in case of epic screw-up, and even then is easily traced. Hoon's capacity for expressing polymorphism, variance, and genericity approaches that of Haskell, though the underlying mechanisms are quite different. The full backend, type inference plus code generation, is about 1,500 lines of Hoon. A Hoon data structure is defined as an idempotent function that normalizes an arbitrary noun. Therefore, defining a structure implies defining a protocol validator for untrusted network data. Types, formats, protocols, and schemas are all the same thing. Hoon's syntax is also unusual and not simple. Hoon works hard to distinguish intrinsic operators from symbols and functions. To avoid write-only code, there are no user-defined macros or other gestures in the DSL direction. Whitespace in Hoon is not significant, as in Haskell. There are no piles of parentheses or other write terminators, as in Lisp. Hoon treats indentation as a scarce resource. Well-indented Hoon with a deep AST flows down the screen, not down and to the right, as in Lisp. Section 2.03, Arbo. The formal state of an Arbo instance is an event history as a linked list of nouns from first to last. The history starts with a bootstrap sequence that delivers Arbo itself, first as an inscrutable kernel, then as the self-compiling source for that kernel. After booting, we break symmetry by delivering identity and entropy. The rest of the log is actual input. The only semantics outside the event history are knock itself plus a functional BIOS, the noun 20302. This noun is a knock function. It calls the first event as a knock function on the rest of the history. The result of this function is the current operating state, a noun. This noun is the Arbo kernel, an object with one method, which is the main event loop. Arbo proper is not large. The kernel proper is only about 600 lines of Hoon. Most system semantics are in kernel modules, veins, loaded as source. User-level code runs either at a third layer within the sandbox vein Gall or a fourth layer within the shell Dojo application. A vanilla event loop scales poorly in complexity. A system event is the trigger for a cascade of internal events. Each event can schedule any number of future events. This easily degenerates into event spaghetti. Arbo has structured events. It imposes a stack discipline on event causality, much like imposing subroutine structure on gotos. User-level code is virtualized within a knock interpreter written in Hoon, with zero virtualization overhead thanks to a jet. Arbo defines a typed, global, referentially transparent namespace with the Ames network identity at the root of the path. User-level code has an extended knock operator that dereferences this namespace and blocks until results are available. So the Hoon programmer can use any data in the urbit universe as a typed constant. Most urbit data is in Clay, a distributed revision control vein. Clay is like a typed GET. Wow, really falling apart here. If we know the format of an object, we can do a much better job of diffing and patching files. Clay is also good at subscribing to updates and maintaining one-way or two-way automatic synchronization. Knock is frozen, but Arbo can hot patch any other semantics at any layer in the system, apps, veins, Arbo, or Hoon itself, with automatic over-the-air updates. Updated code is loaded from Clay and triggered by Clay updates. If the type of live state changes, the new code must supply a function from old to new state. As a solid state interpreter, Arbo is designed to replace both the interpreter and the database in the modern server execution stack. Its event log is its transaction log. It persists by saving dirty pages to a snapshot and/or replaying log entries. Urbit is built with the explicit assumption that a perfectly reliable, low latency, high bandwidth log in the cloud is a service we know how to deliver. The log can be pruned at a reliable checkpoint, however. A non-preemptive OS remains an OS. Every OS needs interrupts. A preemptive OS is interrupted every 20 milliseconds. A non-preemptive OS is interrupted, whether by hand or by a heuristic timer, every time it seems to be taking too long. Interrupted calculations are either abandoned or replaced with an error. Since only completed events are logged, log replay terminates by definition. Ames is an encrypted peer-to-peer network running as an overlay over UDP. Ames does not have separate addressing and identity layers like IP and DNS. An Ames address is an identity mapped to a phonemic string to create a memorable pseudonym and bound to a public key for encrypted communication. Ames addresses are 128-bit atoms. Addresses above 64-bit are hashes of a public key. 64, 32, and 16-bit addresses are initially signed by their half-width prefix. Initial fingerprints of 8-bit addresses are hard-coded. 8, 16, and 32-bit addresses sign their own key updates and are sovereign. Prefix servers are also supernodes for peer-to-peer routing. Ames delivers messages of arbitrary length broken into MTU-shaped fragments. Because urbit nodes are uniformly persistent, they maintain persistent sessions. Message delivery is exactly once. Every message is a transaction, and acknowledgements are end-to-end. The packet-level acknowledgement that completes a message also reports transaction success. A successful transaction has no result. A failed transaction is a negative ACK and can contain an error dump. Ames messages are typed. The type itself is not sent, just a label, like a MIME type, that the recipient must map to a local source path. Validation failure causes a silent packet drop, because its normal cause is a recipient that has not yet received a new protocol update. We want the sender to back off. Ames also silently drops packets for encryption failure. Error reports are just an attack channel. All right, that was section 2. I'm obviously starting to stumble over my words.
You're doing great.
All right, Joshua / Taglix, you want to take a stab at section 3? Before we do that, anything jump out of that last section? We are going to try to go through the details as far as we can get, but
yeah, I had a question. Just how do you understand the statement? This is going back to the clay reference. How do you understand the statement? Clay is like a typed get. What does that mean? A typed get. So how do types play a role in version control or source control?
Sure. So think of the basic sort of decomposed operations in a version control system. Regardless of whether it's snapshot-based or patch-based, the most basic thing is diff, right? You have a file in one state, you have a file in another state, and you need to diff them. The next most basic thing is patch. You have a patch generated from diffing two files, and you want to apply that to a file, right? So there's two operations. And then depending on the system, you could end up with lots of other operations. You could have a sort of patch rewriting, right? Where you combine two patches together. This is sort of like a git rebase or maybe a cherry pick. But there's other operations that are related there, which would be, say, rewrite this patch against this file as if this other patch hadn't been there, that's sort of like an interactive rebase where you remove one of the commits from the ancestry. So just generically speaking, you can figure out what your basic functions would be, if you will, if you were modeling a version control system at a high level. Instead of implementing those functions as transformations on text files.
Yes. Okay.
Clay, it's polymorphic, if you will. It's subtyped. So you have a version of the diff algorithm for a particular type.
That's where we see this in. Is it in Marks? I'm not sure exactly where it is, but you're responsible for being able to support patch and diff, and the code that you provide is responsible for that. Do I understand that correctly? Yep. Okay.
Yeah, there's quite a bit of it supplied with the system itself, but that is a mark. And the best way to think of a mark is that it's an operating system level type.
Okay, so an example of this is let's say I introduce my own media type. It's this great whiz-bang thing, and if you wanted to do some kind of clay-like operations on it, like patch, nobody knows how to do that. I invented this silly structure. I'm probably the best suited to decide how patches function. But the patch operations can be kind of universal. They're generic. We know we're doing a patch or generating a diff. And as the supplier of that MIME type or that mark, I'm accountable for, or my code provides the operations. Is that about right?
Yeah, that's about right. So this is an area of the system that is, I want to speak fairly and precisely, and again, I'm just an outsider. This is an area of the system that is more clearly spec'd than it is clearly implemented. So as it stands right now on the live network, the only marks with a fully fleshed, the only fully fleshed mark is text, basically. So in a sense, right now, Clay gives you the functionality of Git in a different package. The only mark that can fully diff, patch, rewrite patches in the context of other patches, as a fully implemented merge, all of that kind of stuff, is text. There are lots of other marks that are sort of partially implemented. So you can diff them. But for instance, so there's a MIME mark, which is just for arbitrary length encoded atomic data, right? It's like a bit stream. The MIME patch operation is a crash, right? Like it's not, what the MIME type is, that's confusing. What the generic binary type is saying is we don't have any visibility into this data. So if you try to patch them, it doesn't even try, right? So there's a lot of marks. There's XML marks and Markdown marks and HTML marks, and I should qualify what I said earlier. The only totally generic format mark that is fully implemented is text. There are fully implemented app-specific marks. So there are marks for various talk data types for the chat application. There are marks for some of the hood types, the sort of system level types that have diff and patch implementations. But there is not, for instance, a type-aware XML diff and patch.
I see. You know, I have a lot of questions about this, but maybe that's best saved for later because we're kind of getting through the network and then persistence in the subject and whatnot. So I'll hold off other questions. So maybe a later date. So thanks.
Yeah, I hope to be able to do more of these, definitely.
Yeah, it's going to be cool. This is great so far.
All right, Taglix, I'm going to mute and hand it over to you.
Okay, all right. I will take a stab at section 3. So section 3, the solid state interpreter. Let's design a system software stack from scratch. We'll call our design a solid state interpreter, or SSI. urbit is one of many possible SSIs. Briefly, an SSI is an interpreter, which is also a database. In more depth, an SSI combines 3 properties: uniform persistence, source-independent packet networking, and high-level determinism. So 3.1, uniform persistence. Storage in an SSI is flat and uniformly persistent. Uniform persistence is a degenerate case of orthogonal persistence. There is no separation into memory, which is fast but volatile, and disk, which is slow and stable. The system state is one stable data structure. A hardware implementation of uniform persistence could use emerging technologies such as NVDIMMS. Today, urbit runs on normal hardware using a log snapshot mechanism like a normal database. Some low latency stable storage, even just a solid state drive, remains highly desirable. A kernel which presents the abstraction of a single layer of permanent state is also called a single level store. One way to describe a single level store is that it never reboots. A formal model of the system does not contain an operation which unpredictably erases half its brain. It's especially unforgivable to expose this weird split brain design to the user. Modern mobile OSs try to isolate the user from the stateful nature of app instantiation and termination, but never quite succeeds. 3.2, source-independent packet networking. It has no I/O except unreliable, insecure packet networking. HDMI, just an Ethernet cable. USB, PCI. History and not much else. Just a connector issue. There is a categorical difference between a bus, which transports commands, and a network, which transports packets. You can drop a packet, but not a command. A packet is a fact, and a command is an order. To send commands over a wire is unforgivable. You've turned your network into a bus. But networks are magic. Facts are inherently idempotent. Learning fact X twice is the same as learning it once. You can drop a packet because you can ignore a fact. Orders are inherently sequential. If you get 2 commands to do thing X, you do thing X twice. It's possible to layer a command bus, TCP, on top of a packet network, IP, but the abstraction leaks. If the socket closes, has the remote endpoint received my last command? This is a case of the unsolvable two generals problem. Should a systems layer punt n unsolvable problem up to the developer? Another IP mistake is to interpret a packet as a function of its routing topology. A source address is interesting metadata, but it is not data. Fact X means fact X, whoever you heard it from. Packet semantics should be source independent, aka content centric. Logically, we could imagine the ideal network as a global broadcast Ethernet. Everyone hears a packet, everyone hears every packet. Every packet is signed and encrypted. If you have the correct keys to authenticate and decode a packet, you learn from it. Otherwise, you discard it. Independent of topology. 3.3, high-level determinism. Computation in an SSI is defined as a high-level deterministic interpreter. Any computer worthy of the name is deterministic, but its determinism is normally defined as a CPU step function on a memory/register state. If you interrupt an OS defined as a CPU and a memory image, you produce an state. At the high level, such a machine is effectively non-deterministic. High-level determinism is determinism at the semantic level. The operating computation is a function call, not a clock cycle. The system state is a data structure, not a memory image. 3.4, decidability, determinism, and interruption. One Langsec technique is to reduce the expressiveness of a component, such as an input recognizer, to render it more rigorous and tractable. Urbit does not use this trick. It has no sub-Turing calculation model. Can a solid-state interpreter, or any system, be both Turing complete and deterministic/repeatable? This may seem theoretically impossible, but it's actually quite practical. Any practical, non-preemptive OS is interruptible. In exchange for general simplicity across the whole system, the cooperative approach to multitasking pushes the problem of identifying and managing long-running computations up to the programmer. A complex computation can be divided by the programmer into fine-grained subtasks. It can be handled as fake I/O on a worker thread, a feature Urbit doesn't have but should. It can just be a tolerated unavailability period. As CPUs get faster, cooperative multitasking becomes more practical because the length of tolerated unavailability is computed on a human scale. Why we see Node.js returning to the supposedly obsolete design of System 7 and Windows 3.1. But programmers screw up, and an infinite loop is a common bug. Any non-preemptive OS needs a way to interrupt a wayward event. This is easy when the event is a human-generated console event. A secure attention key, for example, Control-C. For all other events, a timer is required. Most events are packets, and network stacks have a lot of timers already. A timer on network packet processing should be seen as a network element. It detects congestion at the CPU level and drops the packet. To the network, an infinite loop is indistinguishable from a cable cut. More important, an interrupted event never happened. deterministic. An event is a transaction. The event log is a log of successful transactions. In a sense, replaying this log is not Turing complete. It's an existence proof that every event within it terminates. Of course, a packet that times out remains a DOS attack. Because AIM's addresses are scarce, DOS attacks via authenticated packets should be relatively easy to track and throttle. 3.5, solid state interpreter, intuitive description. We call an execution platform with these three properties, universal persistence, source-independent packet I/O, and high-level determinism, a solid-state interpreter, SSI. State interpreter is a stateful packet transceiver. Imagine it as a chip. Plug this chip into power a network. Packets go in and out, sometimes changing its state. It loses data and has no concept of a reboot. Every packet is an ACID transaction. A practical SSI, though in a philosophical sense an OS, actually runs as a Unix process. Move down to the hypervisor might be advisable. For low latency determinism, it logs its event stream to a Raft/Paxos cluster. Restore doesn't involve replaying all its history. It periodically flushes dirty pages to a snapshot image. This log and snapshot pattern is the way most modern databases work. Deterministic interpreter can't call out to the OS it's running on. It has to be isolated by definition. In the execution stack, isolated from the legacy OS, has proven useful on the client side. We call it a browser. I'll do it for section 3.
Awesome. So do we want to dive into a little bit of that in some more detail? I put some stuff in the Hangout chat there about Van Jacobson's content-centric networking, which, if not exactly the same, has a lot of overlap with the design of Urbit's network.
So is the idea there that so stars, for example, might be doing some of the routing? Because my question in the chat was, what's the processing overhead, right? If it's a party line, presumably every packet that comes in, you're going to have to make a choice, and presumably that could be expensive. I don't know. Could you DDoS somebody by just blasting them with packets that they can't interpret?
Yeah, you absolutely could. You absolutely could.
So is it correct understanding then that stars, perhaps even galaxies, play some role in making sure that that the packets that are sent down to planets, for example, are the packets that they'll likely be able to interpret?
Yeah, absolutely. Well, they play some role, but not a dispositive role, I guess. Mostly they do peer discovery and some initial routing. What Urbit tries in a wide variety of ways to create a NAT tunnel so that it can communicate directly between two nodes.
Okay.
Once that connection is, it's not really a connection, but once see, this is not my area of expertise, and UDP is connectionless.
Right.
But it punches a hole in the NAT using stun or turn, and then the UDP packets are routed directly between the nodes. So anybody who's on the network, or frankly anybody who is capable of crafting minimally valid looking packets, could DDoS a node just by virtue of knowing that it's running on such and such a UDP port on such and such an IP address. Within the network, the solution there is reputation.
Mm-hmm. Yeah.
You block an identity and you broadcast the fact that you block that identity, and this is not a mechanism that is well established. I think there is some allowance for it.
So let's say that there was some kind of firewalling mechanism, right? So we know we've got a bad actor on the network. I can imagine a couple ways that might be done. It could be up to each individual entity, each individual urbit, to say, I know about this bad actor and I don't touch any packets from them. How they know that packet came from them, we can wave our hands with or at. Or it could be a function of stars that go, hey, I do my best to make sure you don't get any of these bad packets. But if there's peer-to-peer communication, I think in many cases, right? Like, so when I'm in talk, for example, that's all going back up, that's going upstream. I think, right?
Right, but that's because of the design of the talk application where you have a central single host for a channel.
Gotcha. So if I have two apps that want to talk to each other, or I have an app that has, I don't know, some kind of communication mechanism between two urbits, that communication could be peer-to-peer, and then any filtering that would happen would have to be done at the urbit level itself.
That's right. So initial packets will be routed through the stars or even through the galaxies if you're talking about communication between stars. But once the connection, again, I'm speaking vaguely because UDP has no connection state.
Yeah.
Once the peers are able to communicate directly, they do communicate directly. So you are right that sort of a packet level block is the responsibility of the individual nodes, the individual urbit ships or peers or what have you. The role that the hierarchy can play, that stars or galaxies, is by blacklisting the node itself. So once a bad actor is established, say this is a planet, the parent star can say, "Hey, I'm I'm not going to route you, and I'm going to tell everybody that you've been a jerk." Right?
Yeah.
And so now you have to find another star that will host you. And if you're a bad enough actor, then you shouldn't be able to find a star that can host you. Or if you can, that star is probably a bad actor too, and the process just goes up a level.
The dark star, I like to call it.
So it's like a question to expand on that. So like if so like once a connection, I guess like the pseudo connections maybe between two peers, and one of those peers happens to be a bad actor and starts just flooding that other peer with bad packets. Once that peer blocks him, the attacker would just see like blah 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 not found, right? Like they wouldn't be able to see him because essentially you would just like drop your bit to somewhere else, or you block the traffic from the network level or something. I was trying to see like. It seems like the attacker would be isolated pretty quickly from that perspective.
Right. Well, yeah, certainly. And you'd be talking about really like a custom attack mode urbit because the software itself backs off when it can't deliver packets, right? So
Yes.
you have to be making very deep changes in the system to get it to not be backing off in the first place. And if you were being that level of hostile, that's where the other sort of network level mechanisms of reputation and the sort of parent routing table would come in to try to kick you off. That's my understanding. But Pelfin or Tonler, you guys want to jump in on this? The network is actually sort of the area that I know the least about in Urbit.
Yeah, I don't have very much. I don't have a lot of knowledge of the system on that level either, so can't pitch in here.
I was just gonna say it kind of reminds me of like the kind of like node warfare situations you see in Bitcoin, where like nodes are sending each other bad data and then block them throughout the network. It's really, I don't know. It just seems like an interesting like problem that eventually comes up at some point.
Yeah.
Well, eventually, we're gonna have a system in place which will allow blacklisting of ships for certain different types of events. So you could even blacklist a ship for all of its packets. And once you say, hey, I trust you to know what dark ships are and what light ships are, basically, everyone can subscribe to each other's blacklists. And then when a bad actor pops up, someone flags him as a bad actor, and suddenly everyone on the network knows, hey, that's a bad actor, better ignore that guy. So in that way, situations like these can very easily be prevented on a network-wide scale.
So it's like it's almost like an inherent web of trust just by opting in to your identity. Like by having a network address, you're like opting into like a web of trust, so to speak.
Yeah, a developing web of reputation set, right? Because the really important thing is that identities are at least somewhat scarce. Valuable identities are somewhat scarce. Because of course anybody can create as many comments as they want. They'll never come close to exhausting the supply of comments. So by the time the network gets to the state where it's under this kind of attack, comments will start with a very poor default reputation. And so anybody who wants to run scams or to spam or to DDoS or things like that is probably going to need to have a planet. And they're going to very rapidly destroy the value of that planet. So it's unclear what the economics will be, what a planet will actually cost, say, in a couple of years as the network grows. But the idea is there'll be a cost associated with the identity, and that cost should be higher than, you know, whatever value someone can extract from it in a very short period of time before they destroy its reputation.
That was it. That was really cool, though. Thanks.
Hey, did we have some people drop off? Looks like someone's saying the connection dropped from Urbit Meta. I don't know.
Very lovely.
Quick minor question. You mentioned the peer discovery. Is that what the Urbit system refers to as your neighbors?
Yes. Once some identity is your neighbor, then you are able to, you have communicated with them, and you should be able to communicate directly with them. Now, again, the details here are, they frankly elude me, because you can move your ship, right? Your ship is in no way associated with an IP address or a port, you know, or even a Class A network, right? You can move it anywhere. So I'm not sure what the life cycle of sort of peer discovery, and obviously you have to be able to reach your parent to connect to the network, right? So presumably there's some type of chatter between you and your parent ship. So once you come back online and you're on a new port or you're at a new address, then presumably my assumption is that the parent then repeats that sort of whatever initial routing handshake to resume any communication you might have. So it's not exactly the same thing, right? Because once you have neighbored with someone, you will always be their neighbor, right? That's sort of a permanent state. But it doesn't mean you can necessarily communicate directly with them because they may have moved, and so then you need the routing topology to be reestablished.
Sure.
Anything else on section 3? Section 4 is where we really start to get low level here. So let's see. Who else had volunteered? Is that Brian?
Yep, I can do 4.
Awesome.
4.
I'm going to step away real quick and grab a power adapter. I'll be right back. Go for it.
Sounds good. 4. The operating function. An operating function, OF, is a single frozen function that defines the complete semantics of a computer. Not every SSI, as defined above, is an OF, but urbit is. Specifically, the urbit operating function is a lifecycle function, which maps input history to current state. 4.1, lifecycle function. Any SSI needs to define its semantics as a pure function. The obvious way to define a stateful I/O transceiver is a transition function, where function T begins with state and input and leads to state and output. Again, T must be frozen. If we want to change the computer's semantics, it has to be by changing the state. While this transition function will exist in practice, it's not the right way to define our interpreter in theory. First, output doesn't belong to the most fundamental definition of the interpreter. Output is optional. The system can't tell whether its outgoing packets are dropped or delivered. Output is, in a semantic sense, a hint. The transceiver is not ordering a packet to be sent. It is suggesting a packet that might be sent by the runtime system. Second, since the interpreter's semantics are frozen, we might as well take advantage of this to define not just the transition function, but the entire system lifespan as a pure function. The lifecycle function L, consisting of history leading to state, is a more general and useful definition. In practice, any realistic lifecycle function L will have a transition function T somewhere inside it, but the relationship may be complex. 4.2, larval stage. We have 2 problems in designing our lifecycle function L. 1, we need to break symmetry. Even if our network is logically a global party line, and everyone hears every packet, not everyone has the keys to decode every packet. The entropy and/or secrets that establish a node's identity and break symmetry need to be delivered as packets. But they can't be delivered over the party line, then they wouldn't be secrets. Our model seems too simple. There's also a tension between our desire for minimal semantics and the actual complexity of decoding and interpreting packets. Since we're defining the entire interpreter as a frozen function, which is supposed to be a general purpose computer, it should be very obvious that this function never needs updating. So its definition should be very small and simple, ideally fitting readably on a t-shirt. But there is simply no way a small, simple function can decode and interpret packets. For a packet transceiver, this is the entire functionality of the OS. We can imagine a very small OS in a few thousand lines of code, but this is still much too big for a plausible solid-state lifecycle function. Rather, we'd prefer to keep the lifecycle function as a trivial interpreter and deliver the higher levels of the stack, such as a high-level language, an OS, etc., in the packet stream. When we combine high-level code delivery with symmetry breaking, we have 2 problems that both suggest the same solution, a larval stage. Before we plug the newborn node into the network, we feed it a series of bootstrap or larval packets and prepare it for adult life as a packet transceiver on the public network. The larval sequence is private, solving the secret delivery problem, and can contain as much code as we like. But isn't this cheating? If the larval sequence is essential, isn't the true definition of the lifecycle function not L proper, but L plus the larval sequence? It's cheating if and only if the code we deliver in the larval stage can't be updated by later packets in the adult stage. Unless it's so perfect it can be frozen forever, a solid-state interpreter is inherently dependent on remote updates. Another way to describe its invariant is that L is the only non-updatable semantics. Any component above the L level that can be frozen should be. We certainly strive for this ideal. But eliminating the need for a trusted update server is a very long-term goal. Therefore, everything besides L must be remotely updatable. Symmetry breaking, the event that defines the identity of the computer, is exempt from this requirement. Once identity is established, it can't be updated. If you want a new identity, create a new instance. 4.3, step model. Finally, let's relax the criterion that all events are packets. We'll also let the host, OS, send true commands. We'll call this quantum of input, packet, or command a step. A packet can be trivially dropped. A command line has to be handled. It has no default semantics. Also, a packet is a bit string. A command is a symbolic data structure. Intuitively, a packet is a fact, and a command is an order. Commands let the interpreter talk to the host OS. The interpreter is still isolated from the OS, but this just means their semantic definitions are not entangled. An isolated functional interpreter can't call OS APIs in the usual impure fashion. It can process OS commands. In response to these commands, it can suggest actions. Since output is out of scope for L, the real T can do anything. And most real-world OS services can be adapted into this step action pattern. When step processing fails or is interrupted, we can either discard the step or replace it with an error command. For instance, it's very hard to know where code is spinning without a stack trace. This is non-deterministic information by definition. However, one synonym for non-deterministic information is input. We simply write our step history with the crash report, not the original step. If we replay the crash report. And that concludes chapter 4.
So that is a section that I puzzled over for a very, very long time. I think it's a little bit obtuse in its language, but I wonder what everyone else's reaction is.
Brief thought. It seemed to me that the marketing video that was shown during the Star sale was a simpler and more intuitive way to get the same basic concepts across.
But I wonder what everyone else's reaction is.
Yeah, I mean, I echo your.
Marketing video that was shown during the Star sale was a different way to get the same basic concepts across.
Yeah, I think after watching that video and rereading this paper over the last week, this section made a lot more sense. And I'm, although I haven't looked at what actually constitutes the larval stage, I imagine that it is basically injecting into the all of the required functions on the knock VM to actually bootstrap whom, right? So I mean, it makes sense to me. It doesn't seem particularly, it seems magical, but I understand what the point of it is, right?
I had like a kind of a question about the, so like, does this take the place of, say, like private public key encryption? Like, for instance, like this would be like not really a substitute, but this would be like what GPG kind of does in terms of establishing an identity, and you have like your keys, right? So it's almost like generating, like this would be when you want as much entropy as possible, like true random number generation, etc.
I would suggest rather that this is a system that uses public key encryption.
Yeah. So I guess what I'm asking is, like, in terms of making it as secure as possible to the user, you'd want to like generate this on it. Like, would the larval stage be best done on like a secure system, etc. before you? Because once you move the urbit off of that system, then it's good to go. Like, it's frozen. The identity's frozen. So I was just wondering about like the security ramifications, or the security implications of generating it on or what you generate it essentially. If you wouldn't want to generate it like at a library computer, et cetera, you know.
Right. I think that's fair. That's fair to say. I mean, if you're planning on generating a comment and then putting it on your flash drive and taking it with you, yeah, I would think that as long as you clean up your and I don't know exactly what it is that code that gets generated when you start a comment. It's not a public key or a private key, is it? The one that it advises you to delete if you want real security. But yeah, I imagine if you just clean up everything on the computer you're using, you'd be fine, right? I'm not sure, or maybe I'm not understanding the question.
My question would be, no matter how secure the urbit is itself, you're still going to be relying on the security of your Linux server.
Yeah,
right?
that's exactly what I'm asking. It's like the determinism of what keys you get or determine like what kind of entropy you have on the system. For instance, like if you have weak random number generation on your machine or it's compromised, then your urbit keys are compromised by default because it's using public-private key cryptography. So I was just wondering what like security ramifications you'd want to, or what security precautions you'd want to take in order to generate a secure larval state, so to speak. Because a larval state is a place where like urbit can be royally fucked, so to speak, you know? Like where you can be compromised. So I was asking if someone could speak on that.
Yeah, I would go further than that. I would say that right now you should operate as if urbit provides you with very little, if any, protection from your host operating system, if urbit is the guest, to use VM terminology. I think over time, urbit will be able to give you some amount of protection, and maybe an awful lot. But even in the far off future, a dedicated urbit host, say as a service provider, would need a tremendous amount of urbit expertise and would need to take a tremendous amount of care. You know, for instance, the event log is quite simply your urbit, your identity. And you know, it would be trivially destroyed, you know, even by just some simple data corruption. So I think certainly right now, picturing urbit as protecting you from the host operating system is the wrong, it's not something you want to depend on. And
well, I'm not, what my concern is, like, if you're, I mean, I know if the state actor wants to come after you, I mean, I don't think anyone can protect you. But I'm saying, if you back up your urbit, that's fine. But if someone hacks into your Linux server, right, and listens into your password that you're transmitting to get into your urbit, then they have your urbit, right?
yes, absolutely.
So it seems like there's no matter how secure your urbit is, it's really dependent on how secure your Linux host is.
Yes.
And there's, as far as I can tell, there's very little security in Linux hosting right now. In the sense of,
yeah, I mean, there's very little from an end user standpoint, right? Which is why so much of the material here talks about the cloud. The design of this system is such that it is abstracting away for the lower level systems for you, the urbit user, but not for you, the urbit hoster, right? So hosting urbit will require system administration expertise, at least for a very long time. Now, somebody may provide that to you as a service, right? And then you would trust them the way, you know, that you trust AWS right now. But it's still, you know, like your AWS VMs are dependent on the security of the Zen hypervisor. And when somebody busts that thing, like, you know, Amazon patches fast. So we're still in the same world. And, you know, everything at a higher level depends on everything at a lower level. And I don't think, nothing that I've read suggests that we can get away from that. But we can isolate that and, you know, layer it and limit the ways in and so forth. Certainly expert level system administrators can secure Linux hosting, but I'm not sure that I can, and I work on Linux quite a bit, so.
Yeah, I mean, I've never used a Linux command line in my life, really, and I've been setting up a server, and it's like, okay, well, I'm setting my firewall, I guess. I'm just going through these things. What are these chains? I don't know. Let's just set it. It seems, and I understand in the future, even the medium-term future, that's not gonna be a problem. I actually agree. If Urbit takes off, you'll have hosts. That's fine. But the thing that's weird to me is that when you have people who have stars that want to provide network infrastructure in the near term, which you kind of need for the network to start working, and there's really no good infrastructure for those people to have security for their stars, that could be a problem.
Yeah, certainly it could be. So not this next breach, but the next big release, the CC release, will have some recovery mechanisms, right? So that closes one major problem that people have talked about when it comes to hosting. You'll be able to reinstantiate a ship from its private keys, you know, broadcasting to everyone that you effectively had brain damage and you probably don't remember any of your conversations. So that's one thing to keep in mind. But the other thing to keep in mind is that it's a test net, and it's early, right? So another thing that I've seen discussed is the idea of, say, leasing out your stars to some hosting provider. So you come to some kind of arrangement where you don't actually have to run the infrastructure. It is still your infrastructure in a sense, but you've delegated the actual hosting or routing responsibilities to some other sort of provider. And I expect that there will be actually lots of people who want to work on Urbit hosting. But in the meantime, yeah, I mean, it's just a risk that you run, that you have to host it yourself now, basically.
Cool.
Anything else on section 4? I would ask, was the lifecycle function and transition function distinction clear? That was something I puzzled over for a while.
Do you want to maybe give that a few seconds summary? Because I'm there's a lot of this I'm still working through, but I would appreciate another stab at it.
Sure. Yeah, so the transition function is a model of the system as a transceiver, right? So the transition function would take a state and input and produce a new state and output. And that is, in practice, what your Urbit does. I mean, that's basically the simplest literal definition of what it does. But it is not the formal definition of what it does, which is kind of an odd distinction. The formal definition of what it does is the lifecycle function, which is to say that it computes a state from its history. That's the entirety of the formal definition. I think it was back in section 3, or maybe even in section 2. I think I read it. It said that there was it listed a specific knock formula as a kind of functional BIOS, when that was 20302.
Yeah.
And 2 is apply, right? And 0 is slot. It's the tree address dereferencer. So 03 means get the tail of the subject. 02 means get the head of the subject. And that functional BIOS means get the head of the subject and evaluate that as a formula against the tail of the subject, which is the rest of the list. So that knock formula applied to your event history produces your Urbit state. That is the formal definition of Urbit.
Okay.
And
I see. Okay. I get it.
So you get input and output in practice through, they're sort of subsumed into that formal definition, right? So input becomes something that goes into your history, right? And output is a part of the state that can be plucked off by the interpreting environment. But let's see, what was the terminology? Output is, in a semantic sense, a hint. The transceiver is not ordering a packet to be sent, but suggesting it, which is to say that urbit, Arvo, is the host, is the guest, and the interpreter, vir, in the Unix operating system, is the host environment. And without coupling them together, you can't actually make Arvo control its host environment. If you could, then you would have coupled them, right? And we don't want to do that. So output is just data that's provided, and a correct interpreter will do something with it, but there's not sort of this straight line of control. And so output itself is not part of the formal definition of the urbit lifecycle. Does that make sense?
And this is for Arvo in particular.
Well,
will you describe why you don't want to couple those systems, vir and Arvo?
Sorry?
Will you further explain why you don't want to couple those two, vir and Arvo, I think you said?
Yeah, well, so I want to be very careful with what I say here. What I want to distinguish is, right, so there's sort of an inside the urbit worldview, and then there's an outside the urbit worldview, the actual, there's C code and there's system calls and there's UDP packets and all this kind of stuff. So the lifecycle function and the transition function are both models of the formal semantics of the inside the urbit worldview. So you could say that is very technically defined as, knock plus your identity, right? Like those two things together are the unchangeable formal components of an urbit instance.
On the inside.
On the inside, right? And so from the perspective of the inside, the formal definition is simply that very simple knock formula applied to the event history. That's the entirety of the formal definition. So output is nowhere in the formal definition. And input is there inside of the event history, right? So input is a subcategory of the event history.
Mm-hmm.
But from the standpoint, again, of the inside, whether you're looking at it from Knock's perspective or from whom's perspective or from Arvo, is kind of all of those things wrapped together in this formal interface. They can't control, your network device drivers, right? They don't control your TTY.
Okay.
What they do is they produce data structures as part of this transition function, which is sort of buried inside the lifecycle function. They produce these data structures that the outside environment can pluck off. It can grab it and look at it and say, oh, hey, this is a noun with a head of dill. I'm going to send that to the terminal. This is a noun with a head of aims. I'm going to push that out to the, to this UDP socket and so forth. But it's not part of the formal definition, right? Because this is a little bit pedantic, but putting it in the formal definition would sort of entangle it with its outside environment, and it doesn't control its outside environment.
Okay. So it changes it, so the output is just something optional that the outside can choose.
From the perspective of the inside, right?
Yeah.
Obviously, for the urbit user, output is not optional. Right?
And then the implications for that, for the inside, are what? If you
acknowledgement that it can't control it.
Okay.
That it's simply not part of its formal definition, right? So.
Okay, so it doesn't depend on the outside.
Right. Well, it can't control.
Okay.
It. You know, for usefulness, it depends on the outside. Just like for usefulness, it depends on.
Okay, right, sure.
But from within knock, for instance, right? Knock can't control whether or not a particular formula is jetted.
Right.
You know, it doesn't have a dashboard. It can't install or uninstall jets. It can't turn them on or off or anything like that. It just says, here's a formula, you know, I need to evaluate it, right? And it kind of asks the outside environment, evaluate this formula for me. And so a lot of these things are distinctions that matter very much in theory and don't really matter in practice. And that's one of the strange things about this project and about the white paper specifically, because it's so long, right? So you're going and going and going, and you're sort of stuck in this one paragraph here. It's helpful to go back up to the top of the section head. What is this even talking about? Because again, what it's talking about is the formal model of the system, and a lot of this goes back to the all the way back to section 1 with the security argument, which I don't know that this is universally accepted, but it seems pretty bulletproof to me, which is to say that security issues are simply a function of unrigorous computing semantics. As soon as you have unrigorous computing semantics, you have ambiguity, you have variance between implementations, you know, protocol validators, anything else, and that's how attackers get in. I don't know if that's a sufficient formal model of security issues. It seems like there are other things that are left out there, but that certainly is a huge part of them. The Langsec people who are working on formal parsers and things like that, you know, that's the same underlying argument.
So is it safe to say functionality is not guaranteed because we acknowledge we can't control the outside?
Yes, I think so. From the formal perspective of knock, Arvo, absolutely.
Okay, cool, thanks. That's quite clear now.
Maybe from a more pragmatic perspective, not wanting Arvo to be able to function without having to entangle itself with the semantics of I/O is important, because we do want Arvo to be able to run on a crystal ball or positron ring or FPGA one day, right? So maybe Veer, right, will get replaced with an additional vein that will let us communicate in other more efficient ways, right? So I mean, am I kind of encapsulating from a pragmatic perspective what you're saying, Joseph?
Yeah, I think that's absolutely right. And yeah, so much of this project is about designing the simplest possible model for a particular solution to the problem of computing, I guess. It's hard to make it simpler than that. But it really is restricting things in very, very strange ways. And, you know, I've spent a lot of time reading this documentation, and I often find myself scratching my head saying, why go to all of this trouble, right? Like this seems so obtuse. You're jumping through so many hoops to make this thing so absurdly simple, but that's really the whole point, right? And if you just remember, like the goal of this is to make the formal semantics, not like the developer experience or the, you know, the high level programming language or things like that, but the formal model and formal requirements of the system as simple as they can possibly be. I think that ends up answering a lot of questions.
Yeah, thanks.
An interesting question was asked in the talk channel you created. It was by Rovnice Rickfer, and it asks, let me pull this up here. If there shouldn't be a formal definition of the data format that a knock interpreter should be able to speak, so that it knows how to tell on urbit that it's received a packet, and how to understand that an urbit's response includes a suggestion to send some other packet.
Thanks for grabbing that. I'm trying to reread it.
Yeah, what's the question and what's the channel?
So I put some links on the Hangout on the Google Plus event. And there's a web page that shows the channel, but you could also join it in Urbit. It's mardev/whitepaper. You guys got me covered. Thanks.
Got it. Thanks.
So let me see here. Well, so I mean, at the practical level, like this is a very strong critique, which is that Arvo is very minimally documented. There is some documentation on urbit.org, some sort of interface level specs, certainly for some of the data structures, but it is not rigorous and is not complete by any stretch of the imagination. If you end up digging into any of these systems, practically speaking, you are reverse engineering from source, and some of the source is incredibly obscure. I don't think anyone would disagree with that. Some of the defenses of that I've seen in various channels, whether it was all the way back to a Reddit AMA, to some podcast discussions, and feel like I've seen this in various venues, is a firm belief on Curtis's part that early documentation is a big problem, that he does not want to constrain the solution space until he's sufficiently happy with it. So for instance, right now in CC release, a large number, maybe half of the veins are being rewritten or already have been. Ames, I think a Gall rewrite is still scheduled. Arvo itself has been heavily refactored. And so I think that that's a big part of why there hasn't been a larger effort to document some of these things. I spent some time, at one point, I think it was sometime the last fall, I spent a while looking at the veins, trying to decide if I could like document them. And it was just too much reverse engineering work, and I didn't want to try to email people all the time and harass them into trying to give me answers. So practically speaking, I think that documentation will be forthcoming, whether from Tlon itself or from the community. I think a lot of people want that, and the network protocol is a very important part of it. But I think there's a deeper question kind of lurking underneath the practical usability part of saying, hey, you know, I don't want to have to reverse engineer the Ames data structure to be able to write my own interpreter. But at a deeper level, let me think if I can articulate this. In a sense, Urbit plays fast and loose, right? Because you have at core this incredibly formal model. You have, you know, you have knock basically, right? And it's rigorously specified and extensively documented. And then you have this lifecycle function, right? And then there's one layer beyond that, which is the implicit transition function, which is the Arvo interface, right? It's the literal structure of the Arvo core, which is called into directly by address from C in Veer. And that is like the crystalline formal part of it. But there's a whole bunch more of it that isn't like that at all. And the veins are a good example of that. For instance, the terminal, the actual terminal implementation in Veer, in C, is closely coupled to the vein. And it's very difficult to make changes to those kind of systems. They're necessarily coupled. You have to make some changes in Hoon, you have to make some changes in C, you have to coordinate those things very closely together. This is a different critique than Urbit's often criticized for jets, and I don't know if we'll have time tonight, but I hope eventually we can talk about jets, because jets are awesome. But this is different, and I have not seen extensive discussion over sort of the formal nature of veins and the necessary coupling, because basically the entire reason to create a vein is to enable some type of system level functionality within Urbit that requires special functionality outside of Urbit. So for instance, if you wanted to have an IPFS client inside of Urbit, that would make a lot of sense to go inside of a vein. Otherwise you'd be stuck like trying to access IPFS over HTTP or something. But it's kind of a chicken and egg problem, because if you want to write that, then you need to implement actual functionality, you know, in the host environment. And so I don't have a good answer to that. That's just sort of like a necessary compromise with the way the world works. I think over time it will be documented more fully, and it will be much easier to create compatible implementations. But it's still just sort of a necessary compromise with the nature of input and output, I think. I'd love to hear if anybody else has opinions on that sort of coupling.
I'll get back to you on that one.
Sounds good. All right, let's see. So it's 11. I can keep going. Does anybody else keep going? You guys want to? What's next?
I'm down to keep going.
Okay, got energy.
Good.
Let's go.
It's early here.
Right. I keep forgetting that.
Silicon Valley, man, it's the best.
Yeah.
Except for the rents.
Right. It's definitely. All right. So we have section 5, which is knock. This is getting good now. Let me go back and see who volunteered. I think Chaz volunteered to read. You're next on the list, Chaz. You want to read?
I can read section 5. All right. 5, the urbit lifecycle function. Now we're ready to outline urbit's solution to the lifecycle function problem. Let's define L and outline the initial semantics produced by the larval stage, also describing the transition function T. Section 5.1, nouns. The value in urbit is a noun. A noun, oh dear, okay, no, you guys can hear me, right? Okay, take that as a yes. A value in urbit is a noun. A noun is an atom or a cell. An atom is an unsigned integer of any size. A cell is an ordered pair of any two nouns. Nouns are comparable to list S expressions, but are simpler. Sexpers are designed for direct use in a typeless language. Nouns are designed as a substrate for a statically typed language at a higher level. S expressions need dynamic type flags on atoms. For instance, the S stands for symbol, because you can't print an atom without knowing whether it's an integer, a string, a float, etc. If a static type system is expected, these flags are just cruft. For similar reasons, there is no one noun syntax. However, we normally write cells in brackets, bracket A, B, in bracket, that associate right. A, B, C, D means the list of A, the list of B, the list of C, D. Note that AB is not Lisp, but rather cons AB. Right? That is, it's a cons cell, not a list. Noun conventions favor tuples or improper lists, another choice that makes more sense in a typed environment. Real-world S expression systems tend to be leaky abstractions, supporting mutation, cycles, pointer equality tests, etc. The noun abstraction is opaque. For example, equality is a full tree comparison. For fast comparison and associative containers, we do compute a 31-bit lazy Merkle hash on all indirect nouns, but this remains semantically opaque. 5.2, knock. You can think of knock as a functional assembly language. It's a simple combinator interpreter defined by the spec in listing 1. The spec is a system of reduction rules. As appropriate for a system of axioms, it's written in pseudocode. Variables match any noun. Rules closer to the top match with higher priority. A rule that reduces to itself is an infinite loop, which is semantically equivalent to a crash. They're both, and I'm not sure what that symbol is, to be honest. Of course, practical interpreter reports this crash rather than enacting. Knock of A is the full reduction of star A, where A is any noun. Operators. The pseudocode notation defines 5 prefix operators: question mark, plus, equals, /, and star. Question mark of X, the depth test operator, produces 0 if X is a cell, 1 if it is an atom. Plus of X, the increment operator, produces the atom X plus 1 crashing if X is a cell. equals of x and y, the comparison operator, produces 0 if x and y are the same noun, 1 otherwise. Equals x, where x is an atom, crashes. / is a tree addressing operator. The root of the tree is 1. The left child of any node in is 2n. The right child is 2n plus 1. / of x and y is the subtree of y at address x. 0 is not a valid address, and any attempt to take the child of an atom crashes. For instance, / or let's just say tree address 1 of 5412599 is 5412599 as a list, if you will. The tree address 2 of 5412599 is 541. 3 is 2599. 6 is 25, and 12 crashes. All right. Star of x and y is the Knock interpreter function. X, called the subject, is the data. Y, called the formula, is the code. Instructions. A valid formula is always a cell. If the head of the formula is a cell, Knock treats both head and tail as formulas, resolves each against the subject, and produces the cell of their products. In other words, the Lisp program cons xy becomes the Knock formula xy. If the head of the formula is an atom, it's an instruction from 0 to 10. The formula 0b produces the noun at tree address b in the subject. The formula 1b produces the constant noun b. The formula 2bc treats b and c as formulas, resolves each against the formula, resolves each against the subject, then computes Knock again with the product of b as the subject, c as the formula. Without 2, Knock is not Turing complete. In formulas 3b, 4b, and 5b, b is another formula whose product against the subject becomes the input to an axiomatic operator, period. 3 is question mark, 4 is plus, 5 is equals. Instructions 6 through 10 are macros. Deleting them from Knock would decrease compactness, but not expressiveness. 6 BCD is if B, then C, else D. Each of B, C, and D is a formula against the subject. In B, 0 is true and 1 is false. 7 BC composes the formulas B and C. 8 BC produces the product of formula C against the subject whose head is the product of formula B with the original subject and whose tail is the original subject. Think of 8 as a variable declaration or stack push. 9 BC computes the product of the formula C with the current subject. From that product, D, it extracts the formula E at tree address B, then computes star DE. Think very roughly of D as an object and E as a method. 10 BC is a hint semantically equivalent to the formula C. If B is an atom, it's a static hint, which is just discarded. If B is a cell, it's a dynamic hint. The head of B is discarded, and the tail of B is executed as a formula against the current subject. The product of this is discarded. The practical interpreter can do anything with discarded data so long as the result it computes complies with the semantics of Knock. For example, the simplest use of hints is the ordinary debug printf. It is erroneous to skip computing dynamic hints. They might crash. Motivation. Knock is Lisp without upholstery. All user-level features have been stripped for use as a functional assembly language. Syntax, variables, even scope, and functions. Tree addressing replaces the whole architecture of free and bound variables. There's nothing like a GenSim. The Lisp environment, a rare exception to Lisp's homoiconicity, except in very naive Lisps, the environment is not a user-level data structure, is replaced by the Knock subject in ordinary noun. Other typed functional language, such as Tarver's Chi and Shin, have used unmodified Lisps as a compilation target. This is a great strategy for maturity, but it leaves significant simplicity gains uncaptured. Optimization. Or does anyone have any questions we want to stop? This is a pretty hot and heavy stuff. Does it? Don't go once. All right, keep going. The reader may have noticed one problem with knock. Its only arithmetic operation is increment. How can an interpreter whose only arithmetic operator is increment compute efficiently? For example, the only way to decrement n is to count up to n minus 1. Obviously, the solution is a sufficiently smart compiler. It is possible to imagine a special purpose optimizer that analyzed the knock formula and determined that it actually computed decrement. We could also imagine an optimizer for addition, etc. Each of these optimizers would be non-trivial. But a sufficiently smart optimizer doesn't need to optimize every knock formula that could calculate a decrement function. It only needs to optimize one, the one we actually run. This will be the decrement in the kernel library. Any other decrement will be ON, and anyone who rolls their own decrement deserves it. Again, the optimizer need not analyze formulas to see if they're decrements. It only needs to recognize the set of standard decrements which it actually executes. In the common case, this set has one number. To declare itself as a candidate for optimization, the kernel dec function applies a hint that tells the interpreter its official name. The interpreter can check this assertion by checking a hash of the formula against its table of known formulas. The C module that implements the efficient decrement is called a JET. The JET system should not be confused with an FFI, or foreign function interface. A JET has no reason to make system calls, must never be used to produce side effects, and is always bound to a pure equivalent. JETs separate mechanism and policy in knock execution. Except for perceived performance, neither programmer nor user has any control over whether any formula is JET propelled. A JET can be seen as a sort of software device driver, although invisible integration of exotic hardware like FPGAs is another use case. Unlike intrinsic instructions in a classical interpreter design, JETs do not have to be correlated with built-in or low-level functionality. They also can be written in reverse from existing low-level code with tightly defined semantics. For example, urbit crypto is jetted by C reference implementations from well-known libraries. At present, all JETs are shipped with the interpreter, and there is no way to install them from user space, but this could change. JETs are, of course, the main exploit vector for both computational correctness and security intrusion. Fortunately, JETs don't make system calls, so sandboxing policy issues are trivial. But the sandbox transition needs to be very low latency. The knock interpreter written in Rust with Rust JETs is in early development by a third party. A safe systems language like Rust is probably the right long-term solution. L, the lifecycle function. The urbit lifecycle function as a knock formula is 20302. If E is the step history of an urbit instance, the instance's current state is E 20302. This simply uses the first larval step as a formula whose subject is the rest of the step history.
You can pronounce that star as knock if I'm not mistaken.
Knock. Ah, okay. Good to know. Okay. Nice. Thank you. All right. T, transition function. T, the step transition function, is easy to understand now that we know knock. In instruction 9, the C part produces a noun, which is a sort of object, a Hoon core, to get ahead of ourselves. The core, which is in fact the Arvo kernel, is canonically a code data cell. The B part is the address of a knock formula within the core, within VB core, not unlike a vtable index in C++. The intended subject of this formula is the entire core. Our state S is one of these cores. T is a method on the core. The method's product is a new state core S and a list of output actions. It's also easy to see, at least in principle, how we achieve the goal of ensuring that all semantics are updatable. The new core produced by T has to match the knock interface of the old state. In C++ sense, the vtable indexes can't change. Knock can't change. Anything else can change. Hoon could be replaced by a different language so long as it can generate a knock core with the right shape. And there ends section 5.
That deserves a round of applause, man. That's like the most brutal section to read out loud, seriously. Yeoman's work.
Man, no one said there was going to be a whole bunch of algebra in this thing. I don't want to.
The thing with knock is that it's much easier than it looks, but it's very strange relative to, I don't know, anything else that I've seen. And maybe unless you're like a SMK combinator student, I don't know what that would be. Combinatorial something.
Yeah.
It says a lot in documentation that there's no reason, like as a Hoon developer, there's no reason to like dig into knock. But I've heard a lot of people say that if you write your own knock interpreter or figure out how decrement works, that it's like very helpful. So what would you say in terms of like to your students? Like what would you say in terms of getting into knock? Like how deep should?
It depends on what you want to do.
Okay.
Right? Like if you, and Urbit is not, I feel like Urbit's not quite at this point yet, but if you just wanted to sit down with Urbit and write an app, right? The first thing is that you'd have to bug lots of people for like, what are the right moves to, communicate with the network or things like that. But if you just wanted to learn a practical level of Hoon to develop some piece of functionality, learning knock really isn't going to help you in any immediately conceivable way. If you want to learn Urbit, then you should, like you think this is a cool project and you want to learn about how it works, then you should totally go and learn knock. And yeah, I think the best way to do that is to write an interpreter in a language you're comfortable in. I mean, practically speaking, I haven't written a ton of Hoon. I've written a fair amount of Hoon. I haven't thought an awful lot about knock at any point except when I was changing the interface for jets. Then I had to think about knock at a much lower level. And I actually totally had the wrong mental model for how jets work, and was just like flailing around in the dark until I really stopped and thought about it. But as far as not developing kernel level functionality, if you're just developing, generators or apps or writing some glue code, I don't think it helps that much.
I think, personally, I do want to write an interpreter or at least play with somebody else's. But I think learning knock would allow you to then analyze Arvo, which would be fascinating because then you would be able to see how this set of reduction rules can give rise to extremely sophisticated computational operations. And I'm not sure. I'm sure you can go grab Arvo, that little larval stage somewhere, and feed it into your toy interpreter, perhaps, and kind of see how it unfolds. But I think that would be a very good exercise if someone wanted to understand kind of where the magic is with respect to knock. Yeah, I don't know. At least that's somewhere on my short list, my bucket list.
Speaking for myself, I tried to learn Hoon without learning knock first for a while, and most of it made sense, but I found myself running up against what a subject is and what a core actually is, and those suddenly made sense after I played around with knock a little bit just in the dojo.
I would definitely say knock was very helpful for me to understand Hoon better. And what's great about knock is that it takes not really much of an investment at all to make simple little nothing programs. So like just decrement is, once you understand like what you're just counting up to n-1 to decrement from n. Once you understand that, I mean, writing the knock is not that hard, except you actually have to go through and learn the specific. You have to learn like, okay, what's 1 doing, 2 doing, and so forth. But I found it pretty easy, and it really I did find it helpful. I tackled knock before I tackled Hoon though, so it might be that I could have learned the same concepts pretty quickly as I was just learning Hoon. But it takes a little time that I really don't see how it could hurt to at least play with it in Dojo a little bit.
I want to point out to everyone that this is the individual who wrote a knock program that searches for a counterexample to the Goldbach conjecture. And he wrote it in raw knock without knowing who. So take his advice with a grain of salt.
Oh, that's Joseph?
Wait,
That's
Yeah.
Joseph?
is the gentleman who did that among us now?
I wrote the Goldbach program in Knock. That was as taglux nitsep, but okay. In all fairness, though, I had done that for a class earlier, so really it was just taking an algorithm I already knew and was just like, I don't know. It really is not that. It looks really impressive when you see the end product, but actually building it up, it's just little pieces that are pretty simple. But anyway.
Yeah, and Michelangelo just cut figures already existing in the marble out.
Yeah, that's crazy what you do with knock.
I wasn't going to let you get away with that sales pitch. Sorry.
That really is helpful.
I've written
I think it's a
multiple
good
knock
idea.
interpreters. I've written a net dashboard.
Discrediting everything I say because of that program. It was a mistake to release it to the world.
And I don't think I could write that in raw knock. Not without that would just be like a slow manual beating my head against the wall process. Unless I was going to run the compiler in my head, right? Like I could write the Hoon in my head and run the compiler in my head. Man.
Yeah.
Do we have the individual here who wrote the mud in Hoon?
I don't believe he's in here. Maybe he's on YouTube.
No, that would be Elliot, aka Little Ponies. He's not on today.
Was he at the hangout out there at Swan headquarters?
At the meetup, you mean?
Yes.
Yeah, he was at the meetup. He did the Dockhorse presentation.
All right. Any other
All right.
knock questions? Jet questions, maybe?
Actually, I have a knock question. Given that instructions 3, 4, and 5 are simply the operator applied to the simply the operators applied to the interpreter, why do we need the operators at all? Is that just for simplicity of learning it?
There's different ways to answer this question. At the concrete level of the spec, I find the knock spec to be almost incomprehensible. Okay, I know knock, I know how it works, and I still would scratch my head a little bit when I read the knock spec. So like the entire idea of a specification that does not have an associated syntax, but is in its own arbitrarily undefined syntax, I can't quite wrap my head around that. So I can't possibly defend the spec. But I would just say that the operators are abstract, right? And the only way to use them is through the formulas as they're designed, 0 through 10.
Oh, fair enough.
Yeah, I guess is the question about like why do we have like the symbols like the asterisk for the knock and the equal sign when we also have like 5? Is that the question?
Well, the question is, why do we need the question mark, the plus, and the equal sign when we've already got 3, 4, and 5?
So knock is like formula reduction, and the equal sign, the slash, the question mark, those aren't really part of the formulas that are being reduced. Those maybe stand for interpreter states. And that's something that was unclear to me at first too. But yeah, so like the asterisk, the equals, the slash, the question mark, those are ever part of like the when you're messing around in Dojo and you're gonna put raw knock in, you don't put those in. No. Whatever you enter as your knock formula, it's going to like implicitly, and the interpreter says, okay, I'm going to knock this. What has been given to me. You give it a subject, you give it the formula, and then it'll say, okay, I'm going to knock that. I'm going to take this this subject, and then I'm going to apply it to the formula. And really, that's I think what we were talking about earlier, like how there's like this one knock formula that does everything. It's 2, and then what is it, 0, 3, 0, 2, I think it is. Mm-hmm. It's like simulating something related to that. Maybe not exactly, but the idea is that when you're actually writing out knock, you'd use the 5 and I don't know. I think I'm just repeating myself. Sorry.
No, sure.
If I understand it right, which I probably don't, it's just kind of defining the 3 and the 4 and the 5. Because the 3 and the 4 and the 5 are just numbers. They don't really mean anything. And the question mark is saying, okay, or the plus is saying, okay, when you put in this number, it's going to add 1 to it. I don't know. That's how I see it. It's just, I mean, the whole point of the spec is just to explain to us humans. And so I think that's, I don't know, that's what it means to me. It's just saying what those 3, 4, and 5 are going to do.
That makes sense to me. I think that sounds right.
I mean, so 3 is a noun. And the noun 3 refers to the corresponding knock instruction. Is that a fair statement?
Yeah.
Well, kind of. 3 is the corresponding knock instruction, right? Like there isn't really anything by reference.
So it's not like at the knock level, it's not like a macro or something.
Well, 6 through 10 are macros, right? So you can validly implement a knock interpreter just with 0 through 5. You know, and then literally just do the substitutions that are in the spec for 6 through 10. And that works. It computes accurately. And if you look at on the urbit.org docs, there's community knock implementations, and that's how most, at least of the early implementations, actually work. They just do the macros, and that was something that was a really big obstacle to me when I was learning knock. It was like I can't figure out what 8 is doing. I can't figure out what 9 is doing. Right? It's just shuffling these reduction rules, and somehow it works. And so I wrote the JavaScript implementation that's up on the site there, and I put both versions in the interpreter that I wrote. So you have the expansions in there literally, and then you have just sort of a natural implementation of the functionality of each of the instructions. And then it's very easy to see what they do. It's very obvious, you know, like 9, you know, computes a core and then, you know, extracts a formula from the battery of the core and then evaluates that formula against the whole core, right? And like you have to be, I think, pretty sophisticated in your understanding of knock to be able to read the reduction rule and understand that because they're indirect, right? Where's the spec? You know, 9 indirects.
Like and just understand it like right off the bat. I mean, I think everyone has to sit down with a piece of paper or something and like work it out. What does this actually mean if you're actually going to read the spec? Sure.
So there's a couple questions in the chat that I'm seeing here. One of them is about knock integers, and knock integers are natural numbers. Atoms are natural numbers of any size, right? So they don't wrap. They are not, you know, 32-bit, 64-bit, or any other width. They are axiomatically defined as the natural numbers of any size. So that's a huge obstacle to any practical knock interpreter, right? Is that you need, you know, at least a big num library, if not something more complicated. And urbit itself makes heavy use of this property of atoms, right? Anything that works with something analogous to a binary blob in urbit works with a massive atom, right? Because you can think of binary data as an array of bytes or an array of words of some size or a stream of bits, bytes, or words of some size. But if you don't think of them as being separated along some width, you can also think of an arbitrary piece of binary data as just one massive number. And that's what Hoon does. And also, you know, what knock itself does. Let's see, what was the other thing? The other question was about jets. So I would just say that very briefly, my mental model was almost completely reversed because I only learned the bare minimum of knock and then I went straight to Hoon. And if you read the Hoon source, you see these hints all over the place in the kernel for any jetted core, right? Or individual gate or function. Sorry, I have a kid who's crying. I'm going to be right back. I have to go grab somebody. So somebody else take jets. I'll be right back.
That'd be you, Joshua.
I don't really know a ton about jets, to be honest. I I know that things work a lot faster when you write them in Hoon than when you do in raw knock, and that's pretty nice. So, and that for that I like jets, but I mean I don't really understand how they work. Unfortunately, I was looking forward to Dixer's answer.
Perhaps
Anybody else who have a better idea?
Alpha?
No takers?
Maybe since none of us seem to understand it very well, we can read the section over again on jets.
I'm back. Sorry about that. So I'll just summarize very briefly the confusion that I had. So a jet is basically a little bit ambiguous. There's a binding between a knock formula and, say, a native implementation of some kind. In practice, they're all C functions in the current interpreter, but as the spec says it, as the white paper says, it could be FPGAs or, you know, it could be anything, right? It's a substitution, right? It's a special exception saying, you know, compute this formula in some other way instead of just reducing the formula through the knock interpreter. And if you just look at Hoon.Hoon and read the source, you kind of get the impression that the hint is what causes the jet to be called. At least that was the mental model that I built up, because there's a hint in front of every single jetted formula. And it's a little bit more complicated than that for a number of different reasons. But let me just say how it works. And that is to say that there is an interpreter level configuration that lays out a tree of the available jets. And they're structured in it is a tree, they're parent-child relationships. And the reason for that is that the hints are for jet registration. And what that means is the first time the hint is encountered, the tree of potential jets is decorated with metadata about the knock formula, specifically the hash of the formula and pointers to its parent and some configuration for some special use cases. And so the first time it's encountered, the first time the jet hint is encountered, the jet is registered if there is a corresponding actual jet, right? So the formula jet binding is registered if there is a jet. And it's also, I believe, cached if there's not, so that it doesn't pay the lookup penalty every single time. Because the way that this works is every single knock 9 instruction is checked. The hash of the formula itself is checked against this table, the jet dashboard. And if there is a binding in the jet dashboard, then the jet is evaluated and not the formula itself. So that lookup has to be very, very fast, because again, every knock 9, which is to say every time you pull an arm of a core, which is all the time, almost everything that you do is pulling an arm of the core. So that it's a little bit more complicated than what I had assumed just looking at the source, but it's more flexible because you can actually have multiple formulas associated with the same jet. And the reason that you'd want that is, say you compile the kernel in debug mode, so that you have stack traces and things like that if you're working on the kernel. You will end up with a totally different looking formula. It still contains the same logical formula, but it has all of these hints in it that are basically the stack level information associating each line of source, you know, with a file and with a line number and column number and all that, so it can generate stack traces. Excuse me. there's some flags and stuff, you know, so you could end up with a handful of different batteries mapped to the same jet. And that has to work because, you know, without jets, urbit is a joke, you know, like you spin up and start decrementing and you just never stop decrementing. So it's more complicated than you would assume it would have to be, but that's basically why, is that you have to be able to learn about jets over time with variation. The jet bindings that are learned are persisted. They actually go in, I think, the event log itself, but if not, they go next to the event log. So it's a pretty cool system. Anyway, that was longer than I meant it to be. That makes sense? Awesome. All right, Matt, you were gonna take section 6. Anything else on knock or jets before we?
I was just gonna ask. So even in the 1,000 years from now, or whatever, when it's just running on the bare metal, because of some of the inefficiency and decrement and stuff, we would still be going to Unix, but there would be some sort of jet still.
Something like a jet will always be somewhat necessary. Right now, there's a lot of them. There's, I don't remember, 350 of them or something like that. A lot of those wouldn't be necessary. A more efficient interpreter would not need those. But there's always going to be some baseline, because at the very foundational layer, the entire thing is just algorithmically, you know, impossible. You know, again, an OA in decrement, and then all of your mathematical functions are implemented in terms of decrement, right? So like you add two numbers, right? You have a native increment instruction in knock, but for every, you know, you add A and B, for every number less than B, you have to invoke a decrement, because the way that it's coded is that, you know, you add 1 to A and you decrement B, and then you loop until B is 0, and then that's your product. That's how add is implemented, for instance. So everything is implemented basically on top of decrement, which is ON. So at the foundational level, you need some amount of jets, but a really fast, really sophisticated optimizing, you know, JIT compiling interpreter would really only need them for those sort of algorithmically impossible pieces of the system, and I don't think there's that many of them.
So why
Well,
did it
there's.
Go ahead.
Yeah, I was just going to bring up, there's this great discussion on the fora a while ago where PITIP, or PITIP, I don't know how you pronounce these things actually yet, but he was talking about how you could translate it to like nibble code or whatever. Like that's how small knock could be. And honestly, if it given that transition, how easy it is, you know, you get to a point to where you could probably even, you know, make it so that you could interpret, you could put hints into that code as well. And then at the hardware level, you could have, you know, the processor saying, oh, look, here's a hint. I'm going to use my hardware jet or whatever. And especially if there aren't very many of them. I mean, I don't know exactly how that would work. I really, I'm talking about things I don't understand all too well. But really, it doesn't sound like there's any like massive barrier that would, you know, when urbit's having its 1,000-year reign, you know, and hardware manufacturers are, you know, trying to come out with the next thing that'll run this stuff more quickly. It really seems like it would be, I mean, you know, a few innovations away maybe, but definitely doable to have hardware jets that pick up on those hints in the nibble code or whatever. Yeah. I'll see if I can dig up that link. It's an interesting discussion.
So was the determination to exclude decrement, was that an arbitrary choice, or, you know, or was there a reason why it only has increment and then everything else needs to be jetted in order for practicality?
I think on some level it's a little bit of a troll, right?
Okay.
And I'm an outsider here, right? So I'm reading the tea leaves like everybody else. But
Yeah.
there's the early documentation especially seems to relish explaining some of the more improbable aspects of the system, you know, the Lubian inversion and the ON decrement and the spec fits on a t-shirt, and like there's some of this, a lot of this, frankly, I think is aesthetic. And a good comparison is Barpub, who is not in here. Sam Atman has a spec called Axe. And Axe is simultaneously more and less practical than Knock, I think is probably the simplest way to explain it. Definitely look that up. His username is Memion. I think is how you say it on GitHub.
I think he is watching right now.
Barpub, if you're out there, we've got to get you in the group next time so you can talk to us about Axe. Axe includes the basic operations on the natural numbers. And so like it wouldn't have expanded Knock that much to include, say, decrement or to include addition or multiplication even, right? So I don't know how you draw the line, right? Like I'm curious about is what the code compression would look like of different knock operators, different potential knock operators, right? Because that's basically the argument that's in the white paper and in the spec itself, is that the macros 6 through 10 exist for purposes of code compression, right? You could plausibly write a knock interpreter without them. You would just be producing much larger knock formulas because there's so much repetition in those macro expansions, and they're very common patterns. 7 is sort of the more practical eval than 2. 8 is pin, right? So 8 takes a subject, computes a formula against the subject, and puts it at the head of a new subject, and then computes another formula against that, roughly. Anyway, that's close enough. So it's declaring a variable, right? Every time you declare a variable, you're constructing a new subject to compute another formula against. 9 is pulling an arm on a core, so that's just incredibly common. But I'm curious, like, what the ratio of code compression is from those macros, and then what the next most plausible macros might be. I don't think it would be the math, actually, right? Because at a certain point, and I think the best coverage of this topic is the post on urbit.org about the responding to common objections to urbit. And that has at the end a very succinct defense of jets. And the main point of it is to compare jets not against some abstract perfect system, but against practical system, which is to say, an FFI or intrinsic instructions in the VM. And basically the cost that you pay to have jets is that you need an executable specification, right? That's what the knock formula is. That's what the Hoon source is. It's really not that high of a cost for most things. Like, there are exceptions. The markdown parser is pretty complicated and probably not a perfect match. The crypto looks right, but I'm not a cryptographer. So, the more complicated and bigger the jet, the easier it is for there to be some sort of discrepancy. But generally speaking, the things that you're jetting are usually pretty simple functions. You're just jetting them with a much more efficient implementation. And the cost of that over an FFI, well, you don't want an FFI. The whole idea is to seal this thing hermetically. But the cost of that over intrinsic is that you have to have an executable specification. But what it buys you is flexibility going forward, because you can upgrade the system. Anyway, I think I'm rambling now. Does that kind of answer it?
Yeah.
All right, are we ready for Hoon? Is everybody still up to keep going?
I'm good.
Awesome.
Yeah, but in case we start losing people, we should meet weekly or every 2 weeks or something before, in order to get through this.
We don't want to just like marathon with everyone who's willing to keep going. Maybe a cutoff point's a good idea. Because then we'd have like the end, and then some people would be like, "Oh, I would have liked to hear it, but I fell asleep because I'm human." And like you,
well, there's 9 sections total in the doc, right?
Yeah.
Yeah. Aims is divided into 8 and 9, and then 7 is Arvo itself.
Some of them must get quite a bit longer.
Well, another question. Are we able to put this permanently on YouTube afterwards?
I believe it will be, right? So that was one of the things, one of the technical difficulties that I had. And so the first one was that I couldn't just join the original Hangout because I was late. But the second was that I wanted to do Hangouts on air with the live streaming on YouTube. And I believe that I read the YouTube docs properly and, you know, performed the correct incantations on my YouTube account. And at this
No, you definitely did. My sister's watching it live right now. So
I believe it should be hosted permanently in addition to being a live stream right now.
All right, so just marathon then.
At least let's try to get through Hoon, and then we'll reassess.
Yeah, we're not even, we're on page 15.
3 hours ago.
it's E3 tomorrow, man. It's E3.
Joking.
All right. So here we go then. Section 6, Hoon, a strict functional language. Hoon is a strict typed higher order pure functional language which compiles itself to Nock. While Hoon is not much less expressive than Haskell, it avoids category theory and aspires to a relatively mechanical, concrete style. Very rough comparison, Hoon is to Haskell as C is to Pascal. Like C, Hoon is a relatively thin layer over the compiler target, Nock. 6.1, Semantics. The semantic core of Hoon is the backend compiler function mint, which is 1,500 lines of code for type inference and code generation. Mint works with 3 kinds of noun: Nock, a Nock formula; twig, a Hoon AST; and span, a Hoon type, which defines a set of valid nouns and their semantics. The type signature of Mint is buck hep, or with the, let's see, what do you call the first part of the in the parentheses? The span twig.
Oh, that's care.
Oh no.
Oh, sorry, it's kel.
Oh, these here. I mean, kel, and then I'm not sure we pronounce the parentheses and the curly brace in this, do we?
No, I think what you've got is buck, hep, pal, care, span.
Oh, okay. It is. Okay, so say those 2 again. Buck, hep.
Yeah, buck, hep, pal, care, span, twig.
Pal, care. Okay. Span, twig. And then
care.
Care is the same open as closed?
Oh, I'm sorry. No, it's kel and care.
No, it's kel. Yeah.
Kel is open or care is open?
Kel is
kel
open.
for
care is right.
left.
Care is, yeah. L and R for left and right.
Okay, kel, care. Okay. All right, great. Thanks. And then kel, span, knock, care, par. Is that it? And then I don't know what the semicolon is.
Oh, that's sem.
Sen.
Although I think in this case, sem is just part of the text. It's not part of the formula.
Yeah, that's why I was saying, do we even pronounce anything after buck, hep? Because the parentheses and the curly braces in this case aren't runes, right?
No, they are.
They are?
Yeah, they're part of the language.
Oh,
if
okay.
you would type it into the dojo, then it's part of the formula.
Okay.
Yeah, in this case, in this notation, the curly brackets are irregular form for buck call, so $, but the shorthand there is used for just quickly getting the definition down.
Okay.
But I kind of agree with you that, I mean, unless the person that you're reading it to is transcribing it or something, parentheses and the brackets are probably not particularly meaningful.
Well, we're all trying to learn, so it's nice to get them all in. And Joseph said that it's part.
No, I didn't say that.
Sorry.
I applaud, yeah.
I blame it Elfin's fault. I never learned the pronunciation. You know, this is the first time I think I've actually spoken to anybody.
No, this is the best part.
This is awesome.
Yeah, this is the best part of Urbit. I'm happy to finally actually express it with my human mouth.
If the entire project fails, I still hope this catches on.
I think I may just teach my daughter to write using this. You know, just not call it a semicolon at all. Just sem.
Sen. I thought sen was the percent sign though.
Sorry, set. Yes, I meant sem.
Oh, sem. Okay. Roger. And yep, you're correct. Okay, cool. So buck, hep, pal, kel, span, twig, care, kel, span, knock, care, par, sem. That is, mint takes the subject type and the expression source and produces the product type and the knock formula. Understanding the span system gets us most of the way to understanding Hoon. We'll do this in 2 steps. First, we'll explain a simplified version of span, listing 2, that doesn't support adequate polymorphism. Next, we'll extend it to the real thing. 6.1.1, simplified spans. Okay. Well, less, span, right? And then buck.
I think we're good to skip over the listings as we did before. Otherwise, the reading might get really long.
Yeah, all right. Well, we'll just visualize that. I guess. What's the most helpful way to read this, or should we just essentially slide over?
Everyone has a copy of the white paper, right?
Yeah.
Yeah.
Okay.
Let's just skip the listings, and we can refer back to them if
Okay. Buck noun is the set of all nouns. Buck void is the set of no nouns. Kel, buck, cell, p, slash, and just, chime in if you want to, because I don't know all of them. But p/span, q/span, care is the set of all cells with head p and tail q.
Your slash there is FOSS.
FOSS, okay.
You got FOSS and BOSS for forward and backward.
Okay, great. And kel, buck, fork, p, FOSS, kel, set, span, care is the union of all spans in the set p. A buck-hold span with span p and twig q is just a lazy reference to the span of pal, mint, p, q, par. Since Hoon is a strict language, infinite data structures are always expanded manually. A kel, buck, face, p, fos, term, q, fos, span, care wraps the label p around the span q. Remember that Hoon has no concept of scope or environment. Therefore, it has nothing like a symbol table. For a discussion of name resolution, see below. And buck atom is an atom with 2 twists. Q is a unit, Hoon's equivalent of maybe in Haskell, or a nullable in Rust. If Q is, who could fill that one in?
Sig.
Sig, null, 0, any atom is in the span. If Q is cell, sig, X Sir, where X is any atom, the span is a constant. Its only legal value is X. P in the atom is a terminal used as an aura, or soft atom type. Auras are a lightweight advisory representation of the units, semantics, and/or syntax of an atom. Two auras are compatible if one is a prefix of the other. For instance, what's that again? Let's see. Pat T means UTF-8 text, least significant bit low. Pat TA means ASCII text, and Pat TAS means an ASCII symbol. Pat U means an unsigned integer. Pat UD, an unsigned decimal. Pat UX, an unsigned hexadecimal. You can use a Pat UD atom as a Pat U or vice versa, but not as a Pat TAS. But auras are truly soft. You can turn any aura into any other statically by casting through the empty aura Pat. Again, auras are advisory. These definitions are just conventions. Hoon is not dependently typed and can't enforce data constraints. A buck core is a code data cell. The data, or payload, is the tail. Excuse me. The code or battery is the head. P, a span, is the span of the payload. Q, a name twig table, is the source code for the battery. Each twig in the battery source is compiled to a formula, with the core itself as the subject. The battery is a tree of these formulas, or arms. An arm is a computed attribute against its core. All code data structures in normal languages, functions, objects, modules, etc., become cores in Hoon. A Hoon battery looks a bit like a method table, but not every arm is a method in the OO sense. An arm is a computed attribute. A method is an arm whose product is a function. A Hoon function, or gate, is a core with one arm whose name is the empty symbol buck, and a payload whose shape is sir. Is that right? Or is it, no, sorry, cell, right, cell, cell, sample, context, sir. The context is the subject in which the gate was defined. The sample is the argument. To call the gate on an argument X, replace the sample at tree address 6 in the core with X, then compute the arm. Of course, we're not mutating the noun, but creating a mutant copy. 6.1.2, limb.
Want to pause real quick?
Yeah, sure.
That's just, that is a really dense section.
Yeah.
So I want to solicit questions early.
Yeah, good idea.
The pronunciation work that you're doing, I certainly can't or wouldn't be willing.
Happy to do it. Hopefully it's not frustrating to have me look it up.
I had a quick question on, so like for the definition of a span, like, is it like building up from, I guess I'm trying to understand like how it's building up the types, so to speak. It seems like it's saying they're a hint, so they're not actually formal. So like, would this be like, are these like technically informal definitions, or I was trying to like just to see how to think about it, so to speak. Because like, for instance, I remember the other day, Dixer, you showed me that you can reduce all of them to an atom, so to speak, like anything to an atom. So like, I just don't know like how that plays into here in terms of the formal definition of a span.
Sure, I'll take a crack at that. A span is a noun that describes another noun. That's at the absolute base level. So when you say that you have a span, you have a specific noun, you know. This listing 2, in the white paper is a simplified version of the mold for a span. Now, again, the mold is the constructor, if you will. So the syntax that Matt has been reading is not the actual syntax for a span, it's the syntax for the validator for a span. And this was something I didn't get at all, like the first several times through the white paper. This is not the syntax for a span. It is describing the constraints of what makes a noun a span through the lens of the validator. And it's doing that before it's defined the syntax for how you create a validator. So it's very circular. To give a couple of examples, right? So the first thing that wraps the span is the buck pat, which is a mold that represents a fork between an atom or a cell, right? So if what you have is an atom, it's the first child of the buck pat. And if what you have is a cell, it's the second child of it, right? So it's a very simple union type, fork type. If the span is an atom, meaning the noun, the actual noun that we have that is a span, if it's an atom, it has to be either the symbol noun or the symbol void, right? So those are our first two spans. And again, the span is a noun describing another noun. So if we have a span noun, what that means is we don't know anything about this noun. It could be any noun, right? And then void is the opposite of that. It could be no noun, right? So code that produces a span of void is a crash, right? There is no, it doesn't produce anything, right? So if you have an atom and it's a span, it's either the symbol noun or the symbol void, right? So then we move on to the cells. The rest of these span, the rest of our set of possible spans are all cells. And they're tagged. This is a tag union, the buck sen, right? And so what all that means is that you have a bunch of different potential noun shapes, and they're disambiguated by the head of each of them, which is an atom, a symbol. So those symbols could be the symbol atom, the symbol cell, core, face, fork, hold. These are all different types of spans, speaking colloquially, right? And so then, we tried to, the documentation there explains what those different type of spans represent. But the simplest way to think about this is a span is a noun that describes another noun. And for the most part, it's describing the shape of another noun, right? The exception there is the atom span, which is describing the aura, which you could, analogize to the flavor of an atom, right? Which really captures how you intend to use it. But fundamentally, an atom is just an unsigned integer of any size.
So do you usually read a span within a cell in which the span is on the left and the noun that it's referring to, the type of, is on the right of that cell?
Yeah, so that's a face.
That's a face. Okay.
Right. And that's the way that you do dynamic type. Is that you take the static type that the compiler inferred for you, and then you just wrap it up as data. So you have the type and you have the noun.
Yeah.
But it's a good way to look at them, right? And there's syntax for creating them easily in Hoon. And it sort of makes it clear that on the left, like you said, you have the span, and it's actually a noun. And on the right, you have the noun that it describes. Another really good trick is to use 2 question marks in the dojo before an expression. 1 question mark pretty prints the span, right? And spans kind of have their own print format, which is nice and compact, but it's not syntax. It's just a description of the span. But if you use 2 question marks, you get the span as an actual noun. You see it, And so that is very illuminating. Now, it can be very confusing. Some spans get really big really fast. But for simple things, for small nouns, it's really illuminating to evaluate an expression that produces a noun in the dojo, and then evaluate it again, but with 2 question marks and then a space before it. So that would be what ace. Anyway, yeah. So does that help, Stevie?
Yeah, a little bit. I think just learning more about, because I guess it's like a trifecta. You have to know about both molds, spans, etc., in order to know the full type system. So I guess it's kind of like one face of a triangle, so to speak.
Yeah. There's a lot
span
of
is only the
circular
validator.
in the understanding here, and you kind of, at least for me, I had to go over these things, go over and over them before the pieces started to click. But one other thing to note about spans real quick is it's the product of type inference in the compiler, right? So if you think about it very concretely, the compiler analyzes a piece of source code and produces a description of the type of noun that code will produce, right? And so that description has to be a noun itself. The compiler it's written in Hoon, it compiles to Nock, it's all part of the same system. So span is the literal structure of how the compiler describes the type that it infers from a piece of source.
Mm. So the user doesn't define spans.
That's right. Yeah, spans are always produced through type inference and type inference only. Now you can help the type inference along, and that's really what molds are for. Molds are like how you constrain and direct the type inference practically, but you don't have to use them. You can just write code.
I think that's what makes more sense now, is that like it's the compiler that's actually defining the span and not the user or the developer, so to speak.
Right, you're channeling the compiler, right?
Yeah, okay, there we go. That makes, it's starting to make more sense. Because like as you said earlier, like in few days ago, everything reduces down to an atom. So just kind of like maintaining that mentality, I don't know, it does help that way. That's the compiler that's doing the work there. Yeah,
well, I may have. I don't remember saying that exactly, so I might be a little bit confused. From the Nock standpoint, everything reduces down to a noun, but it could be an atom or a cell.
Yes, yeah. So basically, you're just showing me that like pretty much anything that's like, yeah. Sorry, it's like it's a lot to take in, but yeah.
No problem. I just wanted to make sure I wasn't leading you astray.
I also missed the answer to my question. What was that? Do users define spans, or they're purely type inference? Okay.
Yeah, the span is how the compiler represents the product of its inference.
Okay.
Formally. So molds are macros for producing functions or gates that the compiler will infer a specific span for, right? Like, so you use molds, and they have their own syntax, but all they do is produce gates, and then the compiler infers what the product type of the gate would be. And it actually works. I'm not going to live code now because I'm just not going to do it. But you can write raw code, and then just write like a literal anonymous function, if you will, and then cast with it. You use it as a type and cast with it.
Hmm. Okay, that's pretty cool.
Yeah, it is. It's a surprisingly simple system, but it's really difficult to explain.
That's fine.
Thank you so much for the difference between the what and the what, because showing the aura versus showing the actual span.
Right.
Yeah. Really illuminating.
Yeah. For instance, the atom description there, right? It says that buck atom is an atom with 2 twists. I must have read those 3 sentences. I just read them over and over again, and I could not make heads or tails of it. But it's really simple, right? You have either an aura describing any possible atom. All the span is saying is I mean this to be text, or I mean this to be an unsigned decimal integer. Or you have a constant, and then that span is literally saying, I mean this to be, the symbol foo, right? And there's no other atom that will be valid here except for the symbol foo. That's all that's saying, right? So it's in the span itself. And that's what the unit is, the maybe or the nullable. If it's null, then that aura is describing, the set of natural numbers. And if it's not null, then that aura is saying, I mean this specific atom and only this specific atom, right? So you can look at that and say, well, you could actually build up some kind of dependent type system out of constants, and you kind of can, but it's, you have to enumerate the set, if you will. So that's pretty limited.
Now, you keep mentioning symbol, and what do you mean? I mean, I know you're referring to like buck noun or the tilde, which I don't know the actual name for.
Okay, so there's a couple of different things here. Buck noun is a leaf mold. Buck noun is the mold for sen noun. Sen noun is the symbol. And think of it, I don't know if you know Ruby. Ruby has symbols. Lisp has symbols. Think of them as a constrained set of strings that are suitable for naming things. So a string type with constraints. In Hoon, those constraints are lowercase, the leading alpha, alphanumeric, with hep, with a hyphen as a separator. So worm case.
Will you say that one more time? That last part.
The symbol constraint in Hoon is lowercase, leading alpha, alphanumeric, worm case. So hep hyphen is the only valid separator. You can't use underscore. You can't use dots. You can't use slashes. So it's a very, very restricted set of characters, and they're all lowercase, for the symbol constraint. And that's what the aura TAS is.
Okay.
And symbol is a kind of confusing term, but basically, in some programming languages, it means a name that is a string that is suitable for use as a name. If you know lots about XML, you might know like NC name or something like that. It's vaguely similar. So.
Okay, I guess I need to find the link for the documentation on that.
It's light.
It's light. Okay.
Yeah, it's not entirely clear.
But
No,
if
but
you could
sen
name,
noun is the symbol, right? And so
Okay.
what that is that's an atomic string. It's at the same atom as with noun as a chord, right? If you put noun in single quotes and sen noun and you cast them both to act, they're the same number, but the aura is different. And because it's also Hoon syntax, the parser validates the symbol constraint, right? So you could take the string noun all caps and you could cast it to the aura TAS, right? And so then the pretty printer would print sen noun all caps. But if you tried to enter sen noun as Hoon source, the parser would block you. So that's a really good example of the lack of dependent types in Hoon. Like the parsers can validate things, but the type system itself can't. Exactly. Let's see, what else? I don't know if I've gone too far afield. Are there other questions about span?
No, that makes a lot of sense.
I had a question. The hold span. When I was reading this, I just thought, well, that just looks like a quote in Lisp. What is the function or purpose of the hold span?
Hold span is manual laziness. It's concrete laziness, if you want to be a little bit trolly. It's just deferred type inference.
Okay. Yeah. Okay. I dig. I'm sure that'll make more sense later.
Yeah, I don't know that I can explain it practically. I don't know that I know it well enough. It certainly is hard for me to read, and it's hard for me to predict what type of expression will produce what type of hold.
Well, that's a good point in the right direction. I'll make a note of that, and then.
Yeah, I mean, unless you're going to mess with the compiler, all you really need to know is that it is lazy type inference represented concretely, which is to say that you have a subject span and you have a formula twig, which is a parsed expression, and all it's saying is when you get to this point, you need to actually run the inference.
I see. Okay. I got you.
Oh, what's the benefit of that and the con?
The advantage is that you can have infinite spans. The span for a list, for instance, is infinitely recursive.
Okay.
So in a truly lazy language, right, there would sort of be this built-in facility for laziness, right? Like intrinsic to the language itself. Hoon doesn't have that. So when it does something that in Haskell, for instance, which I don't know, so this is all hand wavy. In a case where Haskell would use actual formal laziness, Hoon uses holds.
Okay, well, I don't understand formal versus informal laziness. But,
Well, so in Haskell, right, you can write an expression that produces an infinite set, for instance, or the list of all natural numbers. You can actually write that code, and it's valid code.
Okay.
And then you can say, give me the first 100, and at that point, Haskell will actually do the computation. Right?
Okay. Sure.
So, and it's very lazy. It pushes it defers everything that it can until it's actually needed, right? And my understanding is that in the implementation, there's a tremendous amount of complexity to have this sort of universal laziness and always be deferring computation, right? So there are some problems where you really need to be able to do that. And for those problems in Hoon, the type system uses holds.
So we have the same functionality, it's just different implementation.
We have it in some very specific cases, but not generally, right? Like, so if you tell Hoon, produce me, the numbers 1 through 10,000, it will do that concretely,
Okay.
It will do that before it moves on to the next expression. It will even do that if you pin that list in the subject and don't touch it again.
Yeah. I think I was experiencing that when I generated a bunch of fun
until you actually do something with it.
Yeah. Okay.
I guess maybe another way to put it is that the hold allows Mint to operate on data types that it doesn't know at compile time whether they are ever going to terminate, right? Like just using the example of a list could be infinitely recursive, right? But by deferring the inference, it is somehow, and I don't understand how, but able to surmount that issue. That's kind of what
I think that's mostly right, but it's a little bit, I think you have the infinity in the wrong place, right? The span of the list, well, the type of the list, just colloquially speaking, is infinite, right? The list is either null or a cell. The head of the cell is a list item. The tail of the list is another list, right? So you just have, if your list is not null, or not null, you know, or if you haven't hit a null terminator, you recur, right? So that span is, well, let's say it's potentially infinitely recursive. Now you can't ever have it be actually infinitely recursive. You can't have an infinite list in Vim. You can't do it. But the type system can reason about the list as if it were infinite.
So do you mean you actually can't have an infinite list like you can in Haskell?
Right.
Okay.
In Haskell, you can write code that says, you know, generate, you know,
Right.
literally an impossible data structure, right? Now, if you tried to print it, everything would blow up, for instance. But if you just then, you know, took the first 10 numbers off of it, you know, it doesn't care because it's just a marker saying, you know, by the way, you need to compute these numbers at some point.
Okay.
It's certainly strange coming from other languages. Laziness is weird. And one of the difficult things about the Hoon docs is that they're written for so many different audiences. On the one hand, they're kind of preemptively defending, you know, the language from like these, you know, Haskell gurus, you know, super statically typed, you know, advanced functional programming. And on the other hand, then it's trying to sort of bring along people from like a more traditional object-oriented background. And so like that's really useful because there's all this information there. But if you haven't seen laziness, it's sort of like, what the hell is this?
Yeah.
Also, the docs have this horrible habit of, you know, immediately talking about implementation strategies. Like, I don't know how many people know the implementation strategies of their programming environments, but I can't imagine it's too many.
Well, maybe a few more of us then, at least with regards to Hoon.
Right.
Okay. All right. Well, I'll continue then if
Awesome.
nobody else has anything left. All right. So I believe we're at 6.1.2 limb and wing resolution.
Real quick, I'm gonna sign out right now. So thanks so much for hosting. You guys have a great evening. I'm sure it will be. And I'll see you next time, maybe.
Yeah.
Take it easy.
Later.
Bye, pal. Fun.
I'm gonna sign out too, just because I'm not really asking any intelligent questions at the moment. So I'll just watch it later on YouTube. Thank you guys so much. It was great. See you guys whenever we do it again.
Thank
Take
you
care.
for joining us.
Bye.
Peace.
Yeah, I think I'm gonna. I mean, it's like what, 3 hours? It's 3 hours now. So
It is 3 hours.
after Hoon, then we'll see where we are. So okay, here we go. Understanding spans without any specific knowledge of twigs, for the most part, constrains Hoon enough to understand it in principle. One exception is the limb and wing twigs that reference the subject. An individual reference into the subject is a limb. A limb can be a name like foo, or a tree address like lus13, which is knock fos 13. Again, there are no symbol tables in Hoon. Name resolution is a tree search in the subject, depth first, head first, and cells. There is no separate resolution model for arms and legs. The first match we find, arm or leg, we return. The search is stopped by a buck face unless the limb matches the label. If we find a face foo and we're looking for a bar, we fail instead of looking inside the foo for a bar. But in a core where the search limb matches no arm, we descend into the payload. Okay. A basic name reference returns the first match, but a limb can carry a skip counter expressed by unary. I have no idea what that one is. Anyone know?
That's ket.
By a unary ket prefix, e.g. ket foo to skip 1 foo, ket foo to skip 3, to find deeper matches that have been masked. A wing is a search path, a list of limbs syntactically separated by dot, I'm going to say. Okay. Wings associate right, not left, as in classical languages. Foo.bar.baz in Java is baz.bar.foo, hence baz in bar in foo in hoon. Okay. That's fairly straightforward, but if anybody wants to stop there, then we should too, while we have Joseph here anyways. All right.
Yeah, I don't really think I grok grok it entirely.
Yeah.
So the twig, which has not as of yet been defined in the paper, is a portion of a span. Is that accurate? What is a twig? Let's just go there. What is a twig?
It's an AST, or it's an expression.
Okay.
Right?
Until I think yesterday, I had to look up what AST was. But basically, it's a tree. It's part of the
tree.
The massive universal tree or whatever. The twig is one section of the tree. Is the twig, which again, like kind of like a noun, could go on, or it could be a leaf. I guess if it's a leaf, it's not a twig technically. But anyway.
So we're kind of, so here what we're doing is we're subdividing the various types of the AST for whatever we're computing into types based on their, or into categories based on their function, right? So any portion of an AST which is a reference into the subject is a limb, and then a wing is very similarly to a limb, also a it's just a compound limb, right? It's a set of search paths in sequence. I grok it now, I think.
Yeah.
Yeah, that's right. A limb is a reference of some type into the subject, and a wing is a list of those references to be resolved in, in right to left order.
Awesome. Okay.
And twig is the Hoon AST. AST is abstract syntax tree. It's the parse tree, right? It's the output of the parser. So the parser reads the source, and it generates this structured noun that has all the semantic information from the source in it.
Yeah.
Joseph, is there a, when I read that line about the twig being an AST, I imagine that what the AST was is just some knock, but is there some other intermediate form?
The twig is actually the name of a mold.
But when it says it's an AST, that abstract syntax tree, is that just?
It's just a noun with a particular span.
Okay. Okay.
So it's similar in structure to the structure of span itself, right? It's a tagged union, right? So the name of the twig is that. So twig itself represents a fork between a bunch of different types. There's over 100 of them, right? One for every different type of Hoon expression, And so the type, again, is this fork. It's an array of potential choices. Any valid Hoon expression parses to a valid twig. You know, so there's all of these different potential branches of subtypes within twigs, if you will, but they're all still valid twigs. And for each one of those potentially twig types, you have a tagged noun. So the head of the noun is an atomic symbol, you know, something like cons or call or if. They used to be the pronounceables, right? So they used to be, it would be call hap, you know, or something like that. But when the twig, when the keyword syntax was introduced in Hoon 151, the twig tags all changed to be the keyword for each of the different runes, or not runes, for each of the different twigs, right? So this is another ambiguity in the doc, right? Twig is the name of a Hoon expression. It's the name of a parsed Hoon expression. There's lots of these sort of calculated ambiguities that make sense. You see why they're there once you understand all the pieces, but they don't make it easy to understand the pieces.
I see.
Wait, I thought though that the keywords were added in addition to the runes. They didn't replace them, did they?
No, they didn't replace them, but the structure changed. The structure, the literal representation of the parse tree used to be based on the pronounceables, and now it's based on the names, right? The parser still associates the name and the rune, right? So, you know, it didn't remove the runes from the language, but the representation of parsed Hoon changed.
Why did they do that?
It made the parser simpler once you add the keywords.
Easier to read.
Parser what?
It made the parser simpler. The actual source code of the parser was simpler with, you know, this unified representation that was based first on the keyword.
Okay.
All right.
Wouldn't it be simpler to have a shorter thing? I mean, the one is 2 ASCII characters versus the other one is 4.
Can you talk
No,
to me?
it was the textual representation of the pronounceable. So the head of the would be, you know,
really?
OLHEP.
Oh,
And now it's cons.
wow. Interesting.
Oh, okay.
Oh, why was it ever just the runes themselves? Why, or they couldn't?
No, because it's a tagged union, right? So the whole idea of the tag is that you use a symbolic tag to disambiguate the different potential types, subtypes within an overall type.
So is that the TAS again?
Yes. Yeah, those are symbols.
Yeah. All right. Cool. Should I move on? How about the meta? Let's see. Thing. No. How about YouTube?
I have one quick question. I guess maybe I'm just confused. So I'm trying to see so a core. I guess you explained a gate, but like maybe this will be answered in the future. But like, do you have does the core have to the core payload? I guess not the payload, but the core formula have to fit a specific span or whatnot, or can this be like anything?
It can be anything.
Okay.
The payload has to be specific, right? And the reason for this really is that it's how you. I'm going to back up from that statement. I'm too tired to do a really succinct explanation, of course. The words aren't coming to me. But the span of an arm is always a hold.
Okay, so this expands and it expands and I guess computes until it actually comes to a concrete answer, so to speak. Like you were saying, how a hold that can expand to an actual list, like for instance, the first 100 numbers of real numbers, whatever.
Right. And so the way to look at this is that you can think of the compiler literally pointing to different parts of your program. While the compiler is compiling the core itself, it's inferring holds for the arms of the core. When the compiler gets to the call site where you actually pull an arm out of the core, that's when it actually infers what the type will be of that arm, right? So this is still compile time, right? That's another thing that confused me a lot. And something while we're on the limb and wing resolution, right? I keep reading about this depth first or breadth first search of the subject, and thinking, how can it be that name resolution works this way? And I finally realized that it was talking about compile time, right? Because it's compiling to knock, and by the time it gets to knock, they're just tree addresses. You know, the compiler, you know, it strips the names out completely. It replaces them with knock 0 and a tree address into the subject. So that's what the compiler is the one that is searching the span to see what the address of that you know, portion of the subject will be.
All right, so
I'm willing to try to finish.
I don't know if we're going to be able to get through section 6. There's just so much.
no.
I think we should probably adjourn and come back and do it right. You know?
Yeah, I agree.
Yeah.
Because even if we were going to want to get through 6.1.3, we're still going to have a whole hell of a lot of questions.
Yeah.
So
That's a good point.
I'm tempted to say we should start at 6 next time and just do a little review and then head into new territory.
we did start at 6.
For most people, some
I
people-
think you mean section 6.
Oh, yeah, sure.
Yeah.
I think that's a good idea.
Joseph, thank you so much.
yeah, thank you so much.
Yeah, this has been great.
Yes, very helpful.
Yeah, I've enjoyed it. I've wanted to do some kind of virtual urbit meetup or something for a while.
Yeah.
You're committed to it. You have to do it a lot more often now.
Yeah.
I don't know if I can manage weekly, but maybe bi-weekly could work.
Oh wow,
That's fine.
this is
Yeah.
really in depth. Like at the one meetup, it's great. So
Thanks, everyone.
Cool. And then everybody feel free to add me, because sometimes it is helpful to just chat too. And I'm always in Meta. Everyone's always, let's see. I guess I'm going to post in the fora. If everybody wants to post there or post somewhere, I don't know.
Okay.
And then eventually, I guess Joe will, when he feels like it, schedule another one of these, and we can start where we left off.
Yeah, I think we can talk about it in Meta or comment threads on the fora and try to coordinate another time. I'd like to get to the point where it's a regularly recurring thing, but I don't know what everybody's availability is, and frankly, mine varies a little bit. So
Yeah.
this was great. I certainly want to keep going, and you know, there's community projects that we could look at someday when I'm not so tired. Maybe we could try a little live coding or something. There's all stuff.
Hey, Joseph, you know, you've taken on quite a responsibility here, and you know, if you got some grunt work, or if you need help doing some organization or communication, I'm sure that those of us on the call would be more than willing to help out.
Definitely.
So that you're not stuck doing all the work here. So feel free to use us. I'm volunteering everybody now, but feel free to use me.
Awesome, thank you. I think that's great, and yeah, I mean, I have everybody's names here in the transcript from this, and I don't know. We all know how to find each other at this point, I think. So I won't worry about it too much right now, but we should definitely talk in Meta, on the forum, or come back and comment on the Google Plus event, for crying out loud. And well, we'll work it out. This has been really good, and I look forward to doing some more.
Awesome.
Cool, guys. Nice meeting everybody.
Yep.
Yeah, nice to meet you.
Good night.
Have a great night, everybody.
Yeah, I'm gonna call it.